Hello there and welcome to our channel, where curiosity gets comfortable, science slows its pace, and big ideas are allowed to unfold gently without pressure to arrive anywhere too quickly. This is a place for winding down, for letting the noise of the day soften at the edges, and for following a question simply because it's interesting, not because it demands an urgent answer. Tonight we're going to spend some quiet time with a thought that feels distant, heavy, and strangely calm all at once. A thought about cold. Not the everyday kind that makes you reach for an extra jumper or hesitate before leaving the warmth of your bed, but the deep planetary kind. The kind that reshapes continents, lowers oceans, and quietly rewrites the rules of life on Earth. We're going to talk about ice ages. Not as disasters or headlines, but as recurring chapters in Earth's long, patient history. Because this planet, despite how stable it can feel beneath our feet, has a habit of drifting in and out of colder moods slowly, predictably, almost thoughtfully. It's easy to imagine ice ages as rare catastrophes, like cosmic accidents that happened once or twice long ago and then politely stopped. Mammoths, glaciers, cave paintings, and then modern life arrives and shuts the door behind it. But Earth doesn't work that way. Ice ages are not interruptions in the story. They are part of the rhythm. They come and go, stretch and retreat, advance and pause, all on time scales so long that human history barely registers as a footnote. And the truly curious thing, the part that tends to surprise people, is that we are not living in a world that has escaped them. We're living in a world that is still very much inside one. Before we go any further, take a moment to notice where you are right now. Maybe you're listening from a warm room. Or maybe there's a chill in the air outside. Perhaps it's late evening or early morning, or that soft in-between time when the day hasn't quite decided what it's going to be yet. Where are you listening from tonight? And what does the temperature feel like where you are? Comfortable, cool, heavy, crisp. It's a small thing to notice, but it connects you directly to the story we're about to follow. Because climate at its core always begins as something felt. If this kind of slow, thoughtful exploration feels soothing to you, if you enjoy letting science wander without being rushed toward a conclusion, then you might consider liking the video or subscribing. It helps this quiet corner of the internet find others who could use a gentle pause, too. And now, with that out of the way, let's ease into the question at hand. Earth has entered ice ages before many times, and it will do so again. That statement can sound dramatic at first, even unsettling, but it becomes far less alarming when you begin to understand how these cycles actually work. Ice ages are not sudden freezes that descend overnight. They are not dramatic switches flipped by fate or disaster. They unfold slowly over tens of thousands of years, guided by subtle shifts in sunlight, gravity, oceans, and air. They are the result of Earth responding to gentle nudges, not violent blows. When people hear the phrase ice age, they often imagine a planet locked entirely in ice. Every ocean frozen solid, every continent buried beneath kiln of snow. That has happened in a sense far earlier in Earth's history. But that is not what scientists usually mean when they talk about ice ages today. In modern climate science, an ice age is defined by the presence of large permanent ice sheets on land. As long as massive glaciers exist at the poles, especially in Antarctica and Greenland, Earth is technically in an ice age. The colder and warmer periods within it are called glacial and interglacial phases. Right now, we're in an interglacial, a relatively warm pause, a mild chapter within a much longer cold story. The last major glacial period ended around 11,700 years ago, which in geological terms is barely a breath ago. The ice retreated, sea levels rose, ecosystems shifted, and humans, by coincidence or timing, found themselves in a climate stable enough to settle, farm, and eventually build cities. Civilization did not emerge despite Earth's climate cycles. It emerged during a brief window carved out by them. That window has always been temporary. The idea that Earth periodically cools and warms might feel counterintuitive if you think of climate as something fixed like the background setting of the planet. But Earth is not a static system. It is dynamic, responsive, and deeply interconnected. Small changes in one part of the system ripple outward, amplified by feedbacks that take centuries or millennia to fully reveal themselves. A slight reduction in sunlight at high latitudes can allow snow to linger longer each year. Lingering snow reflects more sunlight back into space. More reflected sunlight leads to further cooling. Further cooling allows ice sheets to grow. And once those ice sheets exist, they begin to shape the climate around them, redirecting winds, altering ocean currents, and locking away vast amounts of water. None of this happens quickly. That slowness is part of what makes ice ages so difficult to grasp intuitively. Human brains are tuned for days, seasons, maybe lifetimes. Ice ages operate on cycles that span tens of thousands of years, driven by astronomical mechanics so steady and predictable that once discovered, they could be calculated forward and backward in time with remarkable accuracy. Long before satellites, climate models, or ice cores, scientists began noticing strange patterns in Earth's geological record. Layers of sediment showed repeated advances and retreats of glaciers. Fossils appeared and disappeared in rhythms that suggested climate shifts, not random chaos. Coastlines seemed to migrate back and forth across continents. At first, these patterns were puzzling. Then slowly, a picture emerged. Earth was not cooling once. It was breathing cold in and out over and over again. One of the most important breakthroughs in understanding this rhythm came from a Serbian mathematician and astronomer named Milankovitch. Working in the early 20th century, often in isolation and without much recognition at the time, he proposed that Earth's long-term climate cycles were driven by variations in its orbit and orientation in space. Not changes in the sun itself, and not sudden shifts in Earth's atmosphere alone, but slow, predictable wobbles in how our planet moves around the sun. Earth's orbit is not a perfect circle. It stretches and relaxes over time, becoming slightly more elliptical and then more circular again. Earth's axis is not fixed upright. It tilts back and forth, changing how strongly the seasons differ. And Earth's axis also wobbles like a spinning top, altering the timing of when seasons occur relative to Earth's position in its orbit. Each of these motions occurs on its own cycle, spanning tens of thousands of years. Individually, they change sunlight only slightly. Together, they can tip the climate system into long-lasting shifts. What matters most is not the total amount of sunlight Earth receives, but where and when that sunlight falls. In particular, summers in the high northern latitudes play an outsized role. If summers are cool enough, winter snow does not fully melt. Year after year, snow accumulates. Over centuries, it compresses into ice. Over millennia, that ice spreads outward, reshaping continents. Once ice sheets reach a certain size, they begin to sustain themselves. Even if the original conditions that help create them begin to change, this is where the story of ice ages becomes less about cold alone and more about memory. Ice has memory. Oceans have memory. Carbon stored in soils and sediments has memory. Earth remembers where it has been, and that memory influences where it goes next. A growing ice sheet lowers sea levels, exposing land that reflects sunlight differently and alters atmospheric circulation. Cooler oceans absorb more carbon dioxide from the air, reducing greenhouse warming and reinforcing the cold. Vegetation patterns shift, further changing how energy moves through the system. These feedbacks mean that Earth's climate does not respond instantly or linearly. It drifts, settles, resists, and then sometimes transitions surprisingly quickly once thresholds are crossed. From a geological perspective, the end of the last ice age was abrupt. Temperatures rose sharply within a few thousand years, which is fast when your usual yardstick is hundreds of thousands. For humans living through those changes, the world would have felt restless. Glaciers retreating, rivers forming, coastlines flooding, ecosystems reorganizing themselves around new rules. And yet, even as the ice retreated, it never fully left. Antarctica remained frozen. Greenland held onto its ice. Earth stayed within the broader ice age pattern. The cold simply loosened its grip for a while. The phrase, "the next ice age is near," can sound ominous if interpreted through a human sense of urgency. Near in this context does not mean next winter or next century. It means that according to the same orbital cycles that have governed Earth's climate for hundreds of thousands of years, the conditions that favor glaciation will eventually return. Left to its own rhythms, Earth would gradually cool again. Snow would persist longer. Ice sheets would begin to grow. Seas would slowly fall. The process would unfold over many thousands of years, long enough that no single generation would witness the full transformation. What makes this moment in Earth's story unusual is not the existence of ice age cycles, but the presence of a new influence layered on top of them. Humans have become a geological force, altering atmospheric chemistry at a pace far faster than orbital cycles operate. Carbon dioxide levels are rising rapidly, warming the planet and counteracting, at least for now, the natural cooling trend that would otherwise be expected over the coming tens of thousands of years. This doesn't cancel Earth's long-term rhythms. It complicates them. It delays some outcomes, amplifies others, and introduces uncertainties that the planet has not experienced before in quite this way. The clocks in the sky are still ticking. The orbits still shift. The tilt still wanders. But the climate system is now responding to both ancient nudges and very recent disturbances. Understanding ice ages, then, is not about predicting a sudden freeze or dismissing current warming. It's about learning how Earth changes when given time. It's about recognizing that stability is often temporary and that the planet's calm periods are not defaults, but intervals created by a balance of forces that never stop moving. For now, just settle into the idea that the ground beneath you carries a long memory, that the climate you experience is one moment in a much larger pattern, and that the cold, far from being an anomaly, has always been one of Earth's most familiar states. When people first hear the phrase ice age, it often lands with a certain dramatic weight, as if it describes a rare catastrophe or a single frozen chapter that once interrupted an otherwise temperate planet. The image that tends to form is simple and stark. Endless snow, woolly mammoths, humans huddled in caves, a world locked in cold until somehow it thawed and moved on. But Earth's relationship with ice is far more familiar, far more repetitive, and far less theatrical than that picture suggests. Ice ages are not accidents or one-off events. They are part of how this planet behaves when given enough time to express itself. To understand what an ice age actually is, it helps to let go of the idea that Earth has a normal climate. There is no default setting that the planet returns to when things settle down. Instead, Earth moves through states, some warmer, some colder, guided by slow forces that don't care whether forests, cities, or coastlines happen to be in the way. In that sense, an ice age isn't Earth misbehaving or breaking pattern. It's Earth following one. In scientific terms, an ice age is defined very simply. If a planet has large, persistent ice sheets on its surface, particularly near the poles, it is considered to be in an ice age. By that definition, Earth is currently in one. Antarctica holds enough ice to raise global sea levels by tens of meters if it were to melt. Greenland remains capped by a thick ice sheet that has survived many warm periods. These frozen regions are not seasonal visitors. They are long-term features anchored in place by geography, altitude, and climate feedbacks that reinforce their existence. What most people think of as the ice age is actually a glacial period within a much longer ice age. Glacial periods are colder phases when ice sheets expand outward from the poles, covering large portions of continents. Interglacial periods, like the one we're living in now, are warmer pauses when ice retreats but does not disappear entirely. These two states alternate not randomly, but rhythmically. Cold advances, warmth returns, ice grows, ice melts back, and through it all, the planet never truly stops being cold at heart. The current ice age began around 6 million years ago, at the start of what geologists call the Plian epoch. Since then, Earth has moved through dozens of glacial and interglacial cycles. Each one has reshaped landscapes, redirected rivers, altered ecosystems, and reset the boundaries of coastlines. The continents themselves haven't changed much in position during this time, but the surface of the planet has been repeatedly rearranged. Mountain ranges have been scraped and smoothed. Valleys have been carved by slow-moving ice. Entire regions have been pressed downward under the weight of glaciers and are still rebounding upward today. What's striking is how calm and methodical this process is when viewed from the planet's perspective. Ice ages do not begin with a dramatic freeze. There is no single winter that signals their arrival. Instead, they creep in quietly. Summers become slightly cooler. Snow lasts a little longer each year. Glaciers stop shrinking and begin to grow almost imperceptibly at first. Over thousands of years, these small changes compound until ice sheets stretch across continents and sea levels fall by more than 100 meters. This gradual nature is why ice ages can be difficult to conceptualize. Human experience is shaped by events that unfold over days, years, or decades. Ice ages unfold over tens of thousands of years. By the time their full effects are visible, countless generations have come and gone. The people living through the early stages of a glacial advance would not have known they were entering an ice age. They would have experienced a climate that felt slightly harsher, slightly less predictable, with ecosystems slowly shifting around them. The big picture only becomes clear in hindsight, recorded in layers of ice, sediment, and stone. One of the most important things to understand about ice ages is that they are not driven by a single cause. There is no solitary switch that flips Earth into a cold state. Instead, ice ages emerge from the interaction of several slow processes that reinforce one another. Changes in sunlight distribution, atmospheric composition, ocean circulation, and surface reflectivity all work together, nudging the climate towards stability or instability, depending on their alignment. At the heart of this system is the balance between incoming energy from the sun and outgoing energy reflected or radiated back into space. Earth's climate is at its simplest level an accounting problem. How much energy arrives, how much stays, and how much leaves. Ice plays a critical role in this balance because it reflects a large portion of sunlight. Snow and ice are bright. They send solar energy back into space rather than absorbing it. As ice spreads, more sunlight is reflected, cooling the planet further and encouraging more ice to form. This feedback loop is one of the fundamental engines of glaciation. But ice does not appear out of nowhere. For glaciers to grow, certain conditions must be met. Winters must deliver enough snowfall, and summers must be cool enough that the snow does not fully melt away. This balance is delicate. A slightly warmer summer can erase a winter's accumulation. A slightly cooler summer can allow snow to persist and gradually compress into ice. Over long periods, these small seasonal differences determine whether ice advances or retreats. The idea that Earth decides to shiver is, of course, a metaphor. The planet does not choose, it responds. And the triggers for those responses often lie far beyond Earth's surface, written into the geometry of its orbit around the sun. Subtle variations in that orbit change how sunlight is distributed across the planet, particularly at high latitudes. These changes do not significantly alter the total amount of energy Earth receives, but they change when and where that energy arrives, which turns out to matter a great deal. When summers in the northern hemisphere become cooler due to orbital variations, snow from the previous winter is more likely to survive. Over time, that surviving snow becomes ice. As ice sheets grow, they influence atmospheric circulation, altering wind patterns and precipitation. They also affect ocean currents, which redistribute heat around the globe. The climate system begins to reorganize itself around the presence of ice, reinforcing the cold conditions that allowed it to grow in the first place. Oceans, in particular, play a quiet but powerful role in ice ages. They act as vast reservoirs of heat and carbon. Cold oceans absorb more carbon dioxide from the atmosphere, reducing the greenhouse effect and allowing temperatures to drop further. Lower carbon dioxide levels make it easier for ice to persist, while expanding ice sheets lock away water, lowering sea levels and exposing continental shelves. These newly exposed lands can change atmospheric circulation and further modify climate patterns. What emerges from all of this is not a single cause, but a system that becomes increasingly comfortable with cold once certain thresholds are crossed. Ice ages are stable states. Once established, they tend to persist until a significant change pushes the system in another direction. That change usually comes from the same place as the initial push. Slow shifts in Earth's orbit that gradually increase summer sunlight in key regions, tipping the balance back toward melting. This push and pull creates the long, sawtoothed pattern seen in ice core records. Long periods of gradual cooling, followed by relatively rapid warming. Ice builds slowly, retreats more quickly, and then the cycle begins again. From a geological perspective, these transitions are remarkably consistent. The timing may vary slightly, but the rhythm remains. It's also worth noting that ice ages are not uniform across the globe. While ice sheets dominate high latitudes, other regions experience different effects. Some areas become drier, others see increased rainfall. Wind patterns shift. Deserts expand or contract. Forests migrate. Ice ages reshape the entire planet, not just the places that end up covered in ice. Even the tropics feel their influence through changes in temperature gradients and atmospheric circulation. Life, of course, does not simply endure these changes passively. Species adapt, migrate, or disappear. Ice ages have been powerful drivers of evolution, repeatedly fragmenting populations and creating new environments. Many of the ecosystems we recognize today were shaped, at least in part, by repeated exposure to glacial cycles. Even humans carry the imprint of these cold periods in their genetic diversity, migration patterns, and early technologies. Understanding ice ages also means recognizing that they are not inherently catastrophic. From Earth's perspective, they're simply different operating modes. The planet has spent more time cold than warm over the last few million years. Warm interglacial periods like the present one are the exception, not the rule. They are valuable windows of stability, but they are also temporary by nature. This perspective can be unsettling at first. There is comfort in believing that the climate we know is the climate Earth prefers. But the geological record tells a different story. Earth is flexible. It tolerates extremes. It oscillates between states without concern for permanence. What feels stable to us is often just a pause in a much longer sequence of change. When scientists say that ice ages are periodic, they are not predicting a sudden collapse into cold. They are describing a long-term pattern that has repeated itself many times. The machinery that drives these cycles is still in place. The orbits still shift. The tilt still wanders. The feedbacks between ice, oceans, and atmosphere still operate. What's different now is the additional influence of human activity layered onto a system that was already complex to begin with. That added influence doesn't erase the concept of ice ages. It interacts with it. It delays some processes, accelerates others, and introduces new uncertainties. But the idea of ice ages remains central to understanding Earth's climate as a whole. Without them, the planet's recent history makes little sense. The shape of coastlines, the distribution of species, and even the timing of human civilization all trace back in one way or another to these long cycles of cold and warmth. So when we talk about Earth entering ice ages, we're not talking about a failure or an anomaly. We're talking about a familiar behavior, one that unfolds slowly enough to seem invisible, yet powerfully enough to leave permanent marks on the planet's surface. Ice ages are not interruptions in Earth's story. They are recurring themes returning again and again, each time slightly different but always recognizable. As this idea settles in, it becomes easier to see the present moment in context. The world outside your window, whatever season it happens to be, is one frame in a very long sequence. The cold has come before. It has retreated before. And the forces that guide those changes are still at work, quietly, patiently shaping what comes next while giving no clear signal of when one phase ends and another truly begins. To understand why Earth slips in and out of icy moods, you have to look far beyond clouds, oceans, or even the continents themselves. You have to look upward, away from weather and seasons, and toward the slow, almost indifferent geometry of space. Because some of the most powerful forces shaping Earth's climate are not storms or volcanoes, but movements so subtle and gradual that they're easy to overlook. Movements that don't feel like motion at all. The planet is always in motion, but much of that motion unfolds at a pace that feels more like drifting than traveling. Earth does not orbit the sun in a perfect frozen pose. It dances slowly, predictably with steps that repeat over tens of thousands of years. This dance is not choreographed for beauty or balance, but it has consequences all the same. The path Earth follows, the angle at which it leans, and the gentle wobble of its axis combine to regulate how sunlight reaches the planet. And sunlight, unevenly distributed, is the quiet architect of ice ages. The first part of this dance involves the shape of Earth's orbit itself. It's tempting to imagine Earth tracing a neat circle around the sun, distance unchanging, energy arriving in steady amounts year after year. In reality, the orbit stretches and relaxes over time. Sometimes it's nearly circular. At other times, it becomes slightly more elongated, more elliptical. This change in shape is called eccentricity, and it operates on cycles that last roughly 100,000 years. When Earth's orbit is more circular, the distance between Earth and the Sun doesn't vary much throughout the year. When it's more elliptical, that distance becomes more pronounced. Earth moves a little closer to the Sun at one point in its orbit, and a little farther away at another. On its own, this change does not dramatically alter the total amount of sunlight Earth receives over a year. The difference is modest, but climate is not just about totals. It's about timing, contrast, and accumulation. An elongated orbit exaggerates the difference between seasons depending on how other factors align. If Earth happens to be farther from the Sun during summer in one hemisphere, summers there become slightly cooler. Winters may be harsher. These small shifts matter enormously when it comes to ice. A cooler summer is often more important than a colder winter. Snow can survive a brutal winter just fine. What determines whether glaciers grow is whether that snow melts away when warmer months arrive. The second step in Earth's slow dance is its axial tilt, also known as obliquity. Earth does not spin straight up and down relative to its orbit. It leans. Right now, that lean is about 23.5 degrees. That tilt is the reason we have seasons at all. It's why summers are warm and winters are cold. Why sunlight strikes different parts of the planet more directly at different times of year. But that tilt is not fixed. Over a cycle of about 41,000 years, Earth's axial tilt shifts between roughly 22 degrees and 24. 5 degrees. When the tilt is greater, seasons become more extreme. Summers are warmer, winters are colder. When the tilt is smaller, seasons are more subdued. Summers are cooler, winters are milder. Again, the key player here is summer. Cooler summers, especially at high latitudes, make it harder for snow to melt completely. Year after year, small patches of surviving snow can accumulate. Ice sheets don't require dramatic cold to grow. They require persistence. A slightly reduced tilt can be enough to tip the balance toward glaciation if conditions align elsewhere in the system. The third motion is perhaps the most subtle and the most poetic in its effect. Earth's axis doesn't just tilt, it also wobbles. Like a spinning top that slowly traces a circle as it spins, Earth's axis gradually changes the direction it points in space. This motion is called precession, and it completes a full cycle roughly every 26,000 years. Precession affects the timing of the seasons relative to Earth's position in its orbit. Right now, the northern hemisphere experiences summer when Earth is slightly farther from the sun. Thousands of years from now, that will reverse. Summer will occur when Earth is closer to the sun, making northern summers warmer and winters less extreme. On its own, precession doesn't change how much sunlight Earth receives in a year. It rearranges when that sunlight arrives. And once again, that rearrangement matters. If precession aligns summer with a point in Earth's orbit that reduces solar intensity, summers cool. If it aligns summer with closer proximity to the sun, summers warm. Ice responds accordingly. What makes this system powerful is not any single movement, but the way these three motions interact. Eccentricity sets the stage by controlling how much Earth's distance from the sun varies. Obliquity adjusts the intensity of seasons. Precession fine-tunes the timing. Together, they create complex patterns of sunlight distribution, particularly at high northern latitudes where large ice sheets are most likely to form. These patterns are known collectively as Milankovitch cycles, named after Milutin Milankovitch, who spent decades calculating how these orbital variations influence Earth's climate. His work was initially met with skepticism. The idea that something as delicate as orbital geometry could drive massive ice sheets seemed implausible to many scientists at the time. The changes in sunlight appeared too small, too subtle. What Milankovitch understood, and what later evidence confirmed, was that climate systems are sensitive. They amplify small changes through feedbacks. Ice reflects sunlight. Cooler oceans absorb more carbon dioxide. Vegetation shifts alter surface reflectivity. Once ice begins to grow, it helps create conditions that favor further growth. The initial orbital nudge does not need to be dramatic. It only needs to persist. Over the last few decades, ice core data, deep sea sediments, and geological records have strongly supported Milankovitch's theory. The timing of glacial advances and retreats align closely with predicted orbital cycles. When summer sunlight in the northern hemisphere decreases due to orbital configuration, ice sheets grow. When it increases, they retreat. The rhythm is not perfect, and it is influenced by many internal processes, but the underlying beat is unmistakable. What's particularly striking is how slow and steady this celestial dance is. These motions are not chaotic. They are governed by gravitational interactions with other planets, primarily Jupiter and Saturn. Their massive pull subtly alters Earth's orbit and orientation over time. The process is so predictable that scientists can calculate past and future orbital configurations with remarkable accuracy. This predictability allows researchers to look forward as well as backward. Based on orbital cycles alone, Earth should be gradually heading toward conditions that favor another glacial period. Summer sunlight at high northern latitudes is decreasing. Without additional influences, this would eventually allow snow and ice to begin accumulating again. But orbital forcing does not act in isolation. It provides the packing, not the entire performance. Earth's climate responds through its own internal dynamics. Oceans take thousands of years to circulate heat. Ice sheets respond slowly to changing conditions. Atmospheric greenhouse gas concentrations rise and fall in response to biological, chemical, and geological processes. This is where the present moment becomes unusual. Orbital cycles operate on tens of thousands of years. Human-driven changes to atmospheric composition are occurring on the scale of centuries. That mismatch in time scales creates tension within the climate system. The slow dance continues, but the music has changed. It's important to be precise here. Orbital cycles do not cause abrupt climate change. They do not explain rapid warming or cooling over decades. They set the long-term boundaries within which climate operates. Think of them as the contours of a landscape rather than the weather passing overhead. They determine whether Earth tends toward cold or warmth over long periods, not how hot or cold a particular decade feels. Still, their influence is profound. Without these cycles, Earth's recent climate history would look very different. Ice ages would not follow the regular patterns seen in geological records. The advance and retreat of ice sheets would lack rhythm. Sea levels would not rise and fall in step with glacial cycles. The migration of ecosystems and the timing of evolutionary pressures would be altered. The slow dance of orbits, tilts, and wobbles also reminds us of something easy to forget. Earth's climate is not solely an earthbound phenomenon. It is shaped by the larger solar system. The gravitational presence of distant planets, the geometry of space, and the mechanics of motion all leave fingerprints on the surface of our world. There is something quietly humbling about that. The shape of a valley carved by ice may ultimately trace back to the influence of a gas giant orbiting far beyond Earth. A glacier's advance may owe its existence to a wobble in Earth's axis that no human could ever perceive directly. The coldest chapters in Earth's history are written in part by motions that never announce themselves. These motions do not pause. They do not adjust for convenience. They continue whether anyone is watching or not. The axis keeps wobbling. The tilt keeps shifting. The orbit keeps stretching and relaxing. Even if the effects are magged or delayed by other factors, the dance never stops. There is a moment in every ice age, though it never announces itself. When snow stops behaving like a visitor and starts acting like a resident, nothing dramatic happens on that first year. No wall of ice appears on the horizon. No global signal sounds. Snow simply lingers a little longer than it used to. A shaded slope keeps its white covering through late spring. A high valley holds onto patches that once vanished by early summer. And then quietly another winter arrives, laying a fresh layer on top of what never quite left. This is how glaciation truly begins. Not with overwhelming cold, but with persistence. Snow is fragile on short-time scales. A single warm week can erase it. A stretch of sunlight can undo months of accumulation. But over long-time scales, snow can become stubborn. When summers grow just cool enough, when sunlight weakens just enough at the wrong time of year, snow gains an advantage. It stops fully melting. And once that happens, Earth's surface begins to change in ways that reinforce the cold rather than resist it. The crucial idea here is that ice ages are not driven primarily by colder winters. They are driven by cooler summers. Winter snowfall is almost always abundant enough at high latitudes and high elevations. What matters is whether summer heat can undo that snowfall. If it cannot, snow survives. Surviving snow compresses under its own weight. Air is squeezed out. Crystals rearrange. Over time, snow becomes firn, and firn becomes glacial ice. And once ice exists, it changes the rules of the climate game. Ice reflects sunlight far more efficiently than soil, rock, vegetation, or water. This reflectivity is known as albedo. A snow-covered surface can reflect back more than 80% of incoming sunlight. Dark ocean water absorbs most of it. Forests absorb it. Bare ground absorbs it. When ice spreads, Earth absorbs less energy. Less absorbed energy means cooler temperatures. Cooler temperatures allow ice to persist and expand. This feedback loop is simple, powerful, and self-reinforcing. At first, the effect is local. A mountain range holds onto more snow. A northern plain stays white a few weeks longer each year. But as ice spreads outward, the scale of reflection increases. Entire regions begin sending sunlight back into space, instead of converting it into warmth. The planet does not cool evenly. It cools preferentially where ice grows. And that uneven cooling reshapes atmospheric circulation. Winds respond to temperature gradients. When polar regions cool relative to the equator, the contrast strengthens. Jet streams shift. Storm tracks migrate. Precipitation patterns change. Some regions become drier. Others receive heavier snowfall. These changes can funnel even more snow into areas where ice already exists, thickening ice sheets and pushing their margins farther south. At the same time, sunlight itself is changing, not in intensity overall, but in distribution. The slow orbital cycles described earlier alter how much summer sunlight reaches high latitudes. When that summer sunlight fades just enough, it removes the primary mechanism that once erased winter snow. The sun still rises. Days are still long in polar summers, but the angle of light is lower. The energy is weaker, the melt season shortens. What makes this especially effective is timing. Snow melt depends on peak summer sunlight, not annual averages. If the strongest sunlight of the year weakens at precisely the time when snow would normally melt most aggressively, the balance shifts. A small reduction in peak energy can outweigh a much larger increase elsewhere in the year. Ice does not care about averages. It cares about thresholds. As snow persists year after year, ice sheets begin to take shape. They are not static slabs. They are slow-moving rivers of ice flowing outward under their own weight. At their centers, ice can become killam thick. At their edges, it grinds across the land, eroding rock, flattening terrain, and transporting enormous amounts of sediment. These ice sheets reshape continents while appearing almost motionless to anything observing them on human time scales. As ice sheets grow, they introduce another important change. They elevate the land surface. Ice sitting on top of continents raises the effective altitude of the surface by hundreds or thousands of meters. Higher elevations are colder, air thins, temperatures drop further. This elevation feedback allows ice sheets to stabilize and expand, even when surrounding regions might otherwise begin to warm. Meanwhile, the oceans are quietly responding as well. When ice sheets grow, they lock away vast quantities of water. Sea levels fall sometimes by more than 120 m during peak glacial periods. Continental shelves are exposed. Coastlines migrate outward. Shallow seas disappear. This changes how oceans circulate heat. Ocean currents act as Earth's long-distance heating system. They move warm water from the tropics toward the poles and return cooler water equator-ward. When sea levels fall and coastlines shift, these currents are redirected. Narrow passages open or close. Shallow seas that once absorbed heat vanish. Cold water expands. And as oceans cool, they absorb more carbon dioxide from the atmosphere. Carbon dioxide is a greenhouse gas. It traps heat. When its concentration in the atmosphere decreases, Earth cools. During glacial periods, atmospheric carbon dioxide levels drop significantly. This is not the initial trigger for ice ages, but it is a powerful amplifier. Cooler oceans draw down carbon dioxide. Lower carbon dioxide weakens the greenhouse effect. Weaker greenhouse warming allows temperatures to fall further. Falling temperatures support expanding ice. The climate system is full of these reinforcing loops. None of them operate instantly. They take centuries and millennia to unfold, but they are persistent. Once several of them align, revering the process becomes difficult without a significant external push. Sunlight fatting at key times, snow refusing to leave, ice reflecting energy away, oceans absorbing carbon, and winds redistributing moisture all begin to work in the same direction. The planet settles into a colder state, not abruptly but decisively. It's important to understand that this does not mean every year becomes colder than the last in a smooth progression. Climate is noisy. Volcanic eruptions can cause brief cooling. Variations in ocean circulation can introduce temporary warmth. Regional patterns can buck global trends, but the long-term direction becomes clear in geological records. Ice advances more often than it retreats. Melt seasons shorten. Ice margins creep outward. This persistence gives ice ages their characteristic shape. They build slowly. Ice sheets take tens of thousands of years to reach their maximum extent. The cooling phase is gradual. The planet resists change, absorbing heat, redistributing energy, and delaying the full expression of orbital forcing. But once ice sheets become large enough, the system becomes primed for a faster transition in the opposite direction. Eventually, orbital cycles shift again. Summer sunlight increases. Peak energy returns at high latitudes. Melt seasons lengthen. Ice sheets begin to thin. Once thinning reaches a certain point, feedbacks reverse. Darker surfaces are exposed. Albedo drops. More sunlight is absorbed. Warming accelerates. Oceans release stored carbon dioxide. Greenhouse warming strengthens. Ice retreats faster than it grew. But that rapid retreat does not erase the memory of ice. Landscapes remain shaped by glaciers long after they melt. Soil distributions change. Drainage patterns shift. Ecosystems reorganize themselves around newly available land and water. Even the planet's crust continues to respond, slowly rebounding upward after being compressed by ice for tens of thousands of years. This lingering influence is why ice ages feel so present even when ice is retreating. The cold leaves marks that persist into warmer periods. Lakes occupy glacial basins. Fertile soils trace back to glacial sediments. Mountain valleys carry the unmistakable U-shaped profiles carved by ice rather than rivers. From the perspective of the climate system, snow refusing to leave is not an anomaly. It is a signal that energy balances are shifting, that thresholds are being crossed quietly, that Earth is responding to a long-term pattern written into its motion around the sun. What makes this process especially subtle is that it doesn't require extreme cold. It requires marginal conditions sustained over time. A few degrees difference in summer temperatures can determine whether ice sheets grow or vanish. A slight reduction in sunlight at the wrong moment can tip the balance. This sensitivity is why ice ages are both predictable in the long term and difficult to perceive in the short term. It also explains why the planet can appear stable while slowly committing to a very different future. From one generation to the next, the climate may feel broadly familiar. Winters and summers still alternate. Plants still grow. Animals adapt. But beneath that familiarity, the accumulation continues. Snow layers thicken. Ice flows outward. Sunlight reflects away. This is why ice ages are best understood not as events, but as processes. They are not moments on a timeline. They are directions the climate system takes when enough small influences align. And once that direction is established, it tends to persist until equally persistent forces push back. Ice ages begin not with overwhelming cold, but with absence. The absence of enough sunlight at the right time. The absence of enough summer warmth to clear away what winter leaves behind. And once that absence becomes routine, the planet responds by leaning into the cold slowly, steadily, without ever needing to announce that a transition is underway. Long before ice sheets carve valleys or coastlines retreat in advance, the oceans begin keeping score quietly, patiently. They do not announce change the way storms do, or signal it with sudden extremes. Instead, they absorb, store, release, and redistribute heat over time scales so long that a single human lifetime barely registers as a moment. If ice ages are the visible expression of Earth's shifting climate, the oceans are the memory that allows those shifts to unfold with rhythm rather than chaos. It's easy to think of the ocean as background scenery, a vast blue surface stretching between continents, mostly unchanged from year to year. But beneath that surface lies one of the most influential systems on the planet. The oceans hold more than 90% of the excess heat in Earth's climate system. They also hold enormous amounts of carbon. And because water changes temperature slowly, the oceans act as buffers, resisting rapid change while quietly committing the planet to long-term trends. When Earth begins drifting toward colder conditions, the oceans do not immediately follow. They lag behind, absorbing the signal gradually, smoothing out sharp edges. This lag is one reason ice ages take so long to develop, even when sunlight weakens and snow begins to persist on land. The oceans continue releasing stored warmth into the atmosphere. This delays cooling. It stretches transitions. It gives the planet inertia. But inertia cuts both ways. Once the oceans cool, they remember that cold just as stubbornly as they once held warmth. Cold water behaves differently than warm water. It is denser. It sinks more readily. As polar regions cool and ice expands, surface waters at high latitudes become colder and saltier. Sea ice formation plays a role here. When sea ice freezes, the ice that forms is mostly fresh. Salt is pushed out into the surrounding water, increasing its density. That dense, salty, cold water sinks, driving deep ocean circulation. This sinking motion is one of the engines of what is often called the global conveyor belt, a vast network of currents that circulate water through the world's oceans. Warm surface waters travel poleward, releasing heat to the atmosphere. Cold, dense waters sink and flow back toward the equator at depth. This circulation moves heat, nutrients, and carbon around the planet, shaping climate patterns on a global scale. During glacial periods, this circulation changes. The formation of extensive sea ice alters where and how deep waters sink. Expanded ice cover limits contact between ocean and atmosphere in some regions, reducing heat exchange. Shifts in salinity and temperature modify current strength. The result is not shutdown, but reorganization. Heat that once traveled efficiently to higher latitudes may be redirected or trapped at depth. These changes matter because they influence how cold spreads and how persistent it becomes. When less heat reaches polar regions, ice has an easier time surviving. When heat remains locked deeper in the ocean, surface temperatures stay cooler. Over centuries, these patterns reinforce glaciation. At the same time, oceans are quietly regulating carbon dioxide. Cold water can dissolve more carbon dioxide than warm water. As global temperatures fall, oceans absorb increasing amounts of carbon from the atmosphere. This drawdown lowers atmospheric carbon dioxide levels, weakening the greenhouse effect and allowing further cooling. It's another feedback loop, slow but powerful. This process leaves behind chemical fingerprints. Tiny marine organisms like plankton build shells from carbon compounds dissolved in seawater. When they die, their shells sink to the ocean floor, accumulating in layers. These layers preserve information about ocean temperature and carbon chemistry at the time they formed. By drilling into deep sea sediment, scientists can reconstruct past climates with remarkable detail. What these records show is a consistent pattern. During glacial periods, atmospheric carbon dioxide levels are significantly lower. During interglacial periods, they rise. The oceans are not the sole driver of these changes, but they are central to them. The actors both sink and source, absorbing carbon during cold phases and releasing it as the planet warms. This release does not happen instantly. As ice retreats and surface waters warm, carbon dioxide slowly escapes back into the atmosphere. This strengthens warming, accelerating deglaciation. Again, the ocean does not initiate the change, but once it responds, it amplifies it. The oceans also influence ice ages through their interaction with sea level. When ice sheets grow, sea levels fall. Vast areas of shallow continental shelf are exposed. These shelves were once active sites of heat exchange, biological productivity, and carbon storage. Their exposure alters coastal currents and changes how nutrients circulate. Lower sea levels also affect the geometry of ocean basins. Narrow passages between continents can open or close. Shallow straits can become land bridges. These changes redirect currents, sometimes dramatically. During glacial periods, altered ocean circulation patterns can isolate regions, creating pockets of cold or warmth that influence regional climates far from the ice sheets themselves. One of the most striking aspects of oceanic involvement in ice ages is how delayed its responses can be. A change in sunlight today might take thousands of years to fully propagate through the deep ocean. Water that sinks in the North Atlantic may not resurface for centuries. This means the ocean is always responding to past conditions as much as present ones. Because of this, climate transitions often overshoot or undershoot before stabilizing. Warming can continue even after the initial cause is weakened, driven by carbon released from oceans. Cooling can persist even as sunlight begins to increase, sustained by cold waters circulating at depth. The ocean acts like a flywheel, maintaining momentum long after the pushes change direction. This is one reason ice age transitions are asymmetric. Cooling tends to be gradual. Warming tends to be faster. Ice builds slowly while oceans resist cooling. Ice melts more quickly once oceans begin releasing heat and carbon. The timekeeper does not tick evenly. It stretches some intervals and compresses others. The biological life within the oceans also plays a role in this timing. Marine ecosystems respond to temperature, nutrient availability, and circulation patterns. Changes in plankton populations affect how much carbon is transferred from the surface to the deep ocean. During colder periods, shifts in ocean productivity can enhance carbon burial, reinforcing low atmospheric carbon dioxide levels. Even the chemistry of seawater changes subtly over glacial cycles. The balance between different carbon isotopes shifts. Oxygen isotope ratios in shells record temperature and ice volume. These chemical clues are among the most reliable records we have of past ice ages, stretching back hundreds of thousands, even millions of years. What emerges from all this is a picture of the ocean as a slow clock. Not one that measures minutes or hours, but one that measures centuries and millennia. Each circulation loop, each sinking plume of cold water, each buried layer of sediment adds a tick. Together, they mark the passage of climate time with a steadiness that land-based processes alone could never achieve. This timekeeping function is why ice ages have rhythm rather than randomness. Orbital cycles provide the packing, but oceans provide the continuity. They ensure that changes are remembered, amplified, and carried forward long enough to reshape the planet. It's also why the present moment is so unusual. The oceans are warming rapidly by geological standards. They're absorbing vast amounts of heat and carbon dioxide at a pace that far exceeds natural ice age transitions. This does not mean the long-term rhythms have disappeared. It means the timekeeper is being pushed hard, storing energy that will influence climate long into the future. That stored energy matters. Even if surface temperatures were to stabilize, the oceans would continue adjusting. Circulation patterns would evolve. Carbon exchange would shift. Sea levels would respond slowly, inexorably. The ocean does not forget quickly. What it absorbs today becomes part of the climate system's future memory. Looking back through Ice Age history, one pattern remains consistent. When the oceans cool, ice advances. When the oceans warm, ice retreats. The relationship is not perfectly synchronized, but it is reliable. Cold oceans support cold worlds. Warm oceans support warm ones. And because oceans change slowly, they give ice ages their characteristic scale. They ensure that these are not fleeting episodes, but extended states that persist long enough to reshape ecosystems, coastlines, and evolutionary pathways. Without oceans acting as reservoirs of heat and carbon, Earth's climate would swing far more wildly, far more often. If ice sheets are the most visible expression of Earth's colder moods, and oceans the slow memory that carries those moods forward, then the atmosphere is the breath that connects everything together. Thin, restless, and seemingly insubstantial, the air surrounding the planet has an outsized influence on how warm or cold Earth becomes. Not because it contains a great deal of heat itself, but because it decides how much heat is allowed to stay. Carbon dioxide, along with a handful of other gases, plays a central role in this decision. It does not create warmth on its own. It does not generate energy. Instead, it acts like insulation, slowing the escape of heat back into space. Change the thickness of that insulation even slightly, and the planet's overall temperature responds. Over short time scales, this response can feel subtle. Over thousands of years, it becomes decisive. One of the most important things to understand about carbon dioxide is that it does not behave like a switch. It is not either present or absent, warming or cooling. It operates on a gradient. Small changes in concentration can shift the balance of Earth's energy budget just enough to favor ice growth or ice retreat. And because carbon dioxide moves between the atmosphere, oceans, land, and living organisms, its concentration reflects the combined behavior of the entire Earth system. During ice ages, atmospheric carbon dioxide levels are consistently lower than during warmer periods. Ice core records show this pattern with striking clarity. As temperatures fall, carbon dioxide declines. As temperatures rise, carbon dioxide increases. This relationship is so tight that for a long time it raised a question that still echoes through climate science. Which comes first, temperature or carbon dioxide? The answer, frustratingly and accurately, is both. Carbon dioxide does not usually initiate ice ages. The initial cooling tends to come from changes in sunlight driven by Earth's orbital cycles. But once cooling begins, carbon dioxide responds in ways that amplify the change. As oceans cool, they absorb more carbon dioxide from the air. Colder water can hold more dissolved gas, and changes in ocean circulation during glacial periods make that absorption more efficient. As carbon dioxide is drawn down, the greenhouse effect weakens, less heat is retained, temperatures fall further, ice expands more easily. This feedback loop is one of the reasons ice ages, once underway, become stable. The atmosphere adapts to the cold by reducing its capacity to trap heat. In effect, the planet's breath grows thinner, allowing warmth to escape more freely. The mood shifts toward cold, not abruptly but persistently. Land processes contribute as well. During glacial periods, vegetation patterns change dramatically. Forest retreat. Grasslands expand or contract. Large areas become tundra or desert-like environments. These shifts alter how much carbon is stored in soils and plants. Colder, drier conditions tend to slow decomposition, allowing organic matter to accumulate in some regions while reducing it in others. The net effect often favors carbon storage outside the atmosphere. Dust also becomes more prominent during ice ages. As glaciers grind rock into fine particles and winds strengthen overexposed continental shelves. Dust is carried into the atmosphere and deposited over land and sea. This dust can fertilize ocean ecosystems by delivering iron and other nutrients. In some regions, this stimulates plankton growth, increasing the transfer of carbon from the surface ocean to the deep sea. That carbon is then effectively removed from the atmosphere for long periods. Once again, no single process dominates. The decline in atmospheric carbon dioxide during glacial periods emerges from many small contributions acting together. Oceans absorb more. Land stores more. Biological processes shift. Dust alters productivity. The result is a gradual but significant reduction in greenhouse warming. What's important is that carbon dioxide changes do not simply follow temperature. They reinforce it. When the planet begins cooling, carbon dioxide responds in ways that encourage further cooling. When warming begins, the reverse happens. As ice retreats and oceans warm, carbon dioxide slowly returns to the atmosphere. Warmer water releases dissolved gases. Changes in circulation bring carbon-rich deep waters back to the surface, where they exchange carbon dioxide with the air. Vegetation spreads into newly available land, altering carbon storage. Soils that were frozen or dry begin decomposing more actively, releasing carbon. This release strengthens warming. The atmosphere thickens its insulating layer. Heat escapes more slowly. Temperatures rise faster than orbital forcing alone would predict. This is why deglaciation often appears abrupt in the geological record. The initial increase in sunlight begins the process, but carbon dioxide accelerates it. Ice core data reveal this pattern clearly. During the transition out of the last major glacial period, atmospheric carbon dioxide rose by about 80 parts per million over several thousand years. That increase may sound modest, but it was enough to transform the planet. Ice sheets collapsed. Sea levels rose. Ecosystems reorganized. The climate shifted into a new mode. It's worth pausing to consider the scale of these changes. An 80 parts per million increase spread over thousands of years reshaped the Earth. Today, atmospheric carbon dioxide has risen by more than that amount in just a couple of centuries. This comparison is not meant as an alarm in this context, but as a reminder of how sensitive the climate system is to relatively small changes in atmospheric composition. During ice ages, carbon dioxide acts as a stabilizer for cold conditions. During interglacial periods, it acts as a stabilizer for warmth. It does not determine the timing of transitions, but it determines how far and how fast those transitions go. Another key feature of atmospheric carbon dioxide during ice ages is its global reach. Unlike ice sheets or ocean currents, which have strong regional expressions, carbon dioxide mixes throughout the atmosphere. A change in concentration affects the entire planet. This makes it a powerful amplifier of any initial forcing. Because of this, ice ages are global phenomena, even though their most dramatic effects occur in specific regions. Tropical temperatures shift. Monsoon patterns change. Deserts expand or contract. Rainforests migrate. The entire climate system adjusts to a new baseline set in part by atmospheric composition. The atmosphere also interacts with ice directly in ways that are easy to overlook. As ice sheets grow, they alter atmospheric circulation patterns. Massive ice domes create high-pressure systems. Winds flow around them, redirecting moisture and heat. These wind patterns influence where snow falls and where it doesn't, shaping the geometry of ice sheets. Colder air holds less moisture. During glacial periods, the atmosphere becomes drier overall. Snowfall decreases in some regions even as ice sheets expand. This seems counterintuitive, but it reflects the complexity of the system. Ice sheets grow not because snowfall increases everywhere, but because melting decreases more than snowfall does. The dryness of glacial atmospheres also affects dust transport, cloud formation, and radiation balance. With less water vapor, one of the most potent greenhouse gases, the atmosphere loses additional heat-trapping capacity. This further cools the planet. Again, small changes compound. Ice cores provide a direct record of these atmospheric changes. Tiny bubbles of ancient air trapped in ice preserve snapshots of past atmospheres. By analyzing their composition, scientists can see how carbon dioxide, methane, and other gases varied over time. These records show repeated cycles of low greenhouse gas concentrations during glacial periods and higher concentrations during interglacials. Methane, while less abundant than carbon dioxide, also plays a role. Its concentration drops during ice ages, likely due to changes in wetlands, permafrost, and biological activity. This contributes additional cooling. The combined effect of reduced carbon dioxide, reduced methane, and reduced water vapor creates an atmosphere that allows heat to escape efficiently. It's important to emphasize that these atmospheric changes are responses, not independent drivers. They're woven into the broader climate system. Orbital changes alter sunlight. Ice and oceans respond. The atmosphere adjusts. Feedbacks amplify the direction of change. This interconnectedness is what gives ice ages their coherence. Each component reinforces the others. None acts alone. Remove any one piece, and the system behaves differently. The phrase breathing carbon captures something essential about this process. Over glacial cycles, Earth inhales and exhales carbon dioxide. It draws carbon into oceans, soils, and sediments. During cold periods, it releases carbon back into the air during warm periods. This breathing is slow, measured in thousands of years, but it is remarkably regular. That regularity allowed scientists to identify the pattern long before they fully understood the mechanisms. Carbon dioxide rises and falls in step with temperature. The planet's mood shifts accordingly. What complicates the present moment is that this breathing has been disrupted. Carbon is being added to the atmosphere faster than natural processes can absorb it. Oceans are taking up much of this excess, but not without consequence. Warmer waters absorb less carbon dioxide. Circulation patterns change. Acidification increases. The atmosphere thickens more rapidly than it has during past interglacials. This does not mean ice age cycles have vanished. The long-term orbital rhythms are still operating, but the baseline has shifted. The atmosphere's insulating layer is stronger than it would otherwise be at this point in the cycle. That added warmth delays the conditions that would normally allow snow to persist and ice to grow. From a long-term perspective, this delay could last tens of thousands of years. Eventually, orbital forcing may overwhelm even elevated greenhouse gas concentrations. Or human activity may alter the system in ways that change its future behavior entirely. The climate system has never experienced this exact configuration before, which makes precise predictions difficult. Still, the role of atmospheric carbon dioxide in ice ages remains clear. It is not the conductor of the orchestra, but it is a powerful amplifier of whatever tune is being played. When the melody bends toward cold, carbon dioxide deepens it. When the melody bends toward warmth, carbon dioxide carries it farther. The sky above you is not just a backdrop. It is an active participant in Earth's long climate story. With every molecule of carbon dioxide added or removed, the atmosphere quietly adjusts how much warmth is allowed to linger, nudging the planet toward cold or warmth with a patience that matches the scale of ice ages themselves. Ice sheets are often imagined as blank, lifeless expanses, vast white surfaces that exist only to reflect sunlight and chill the air above them. From a distance, they appear empty, even forgetful, as if nothing ever really happens there. But this impression could not be more misleading. Ice sheets are among the most detailed record keepers on the planet. They remember far more than forests or oceans ever could. Not because they are alive, but because they are patient. They grow slowly, layer by layer, year after year. And in doing so, they trap an extraordinary amount of information about the world that existed when each layer formed. Every snowfall that lands on an ice sheet is a small historical event. Snow carries with it particles from the atmosphere, tiny traces of dust, salt, pollen, volcanic ash, and gases. As that snow is buried by subsequent snowfalls, it is compressed. Air pockets become sealed. Layers thin and harden. Over time, loose snow becomes firn, and firn becomes solid ice. Once sealed, those air bubbles and particles are locked away, sometimes for hundreds of thousands of years. This process turns ice sheets into time capsules, not in the metaphorical sense, but in a literal one. The air trapped inside ancient ice is real air, once breathed by plants, animals, and oceans long gone. The dust tells stories about winds and deserts. The chemical composition of the ice reveals temperatures, precipitation patterns, and even the intensity of sunlight reflected back into space. When scientists drill deep into ice sheets and extract long cylinders of ice, they're pulling out a layered archive of Earth's climate history. What makes ice sheets especially valuable as climate records is their continuity. Unlike sediments on land, which can be eroded, disturbed, or destroyed, ice sheets accumulate in a relatively orderly fashion. Each year adds a new layer. In places where ice persists for long enough, those layers stretch back through multiple glacial cycles. The deepest ice near the center of major ice sheets can be more than 1 million years old. Two regions dominate this frozen archive: Antarctica and Greenland. These ice sheets exist because of geography as much as climate. Antarctica sits over the South Pole, isolated by powerful ocean currents that limit heat exchange. Greenland, while closer to temperate regions, rises high enough above sea level that cold conditions persist even during warmer periods. Together, they anchor Earth's ice age status. Within these ice sheets, memory is stored in multiple ways at once. One of the most direct is through oxygen isotopes. Water molecules contain oxygen atoms, and those atoms come in slightly different forms called isotopes. Some are heavier than others. When water evaporates from the ocean, lighter isotopes evaporate more easily. When it cools and falls as snow, heavier isotopes are more likely to be left behind. The ratio of these isotopes in ice depends on temperature. Colder conditions favor a different balance than warmer ones by measuring the ratio of oxygen isotopes in each ice layer. Scientists can estimate the temperature at the time the snow fell. This method has been refined over decades and provides one of the most reliable temperature records available for Earth's past. Ice also records greenhouse gases directly. The tiny bubbles trapped within ice contain samples of ancient atmospheres. By crushing the ice in controlled conditions and analyzing the released gases, scientists can measure past concentrations of carbon dioxide, methane, and other trace gases. These measurements show with striking consistency that greenhouse gas levels rise and fall in step with temperature over glacial cycles. What makes this especially powerful is the precision of the timing. In some ice cores, individual annual layers can still be distinguished, at least for the more recent past. Even deeper down, where layers thin and merge, careful analysis allows scientists to reconstruct timelines with remarkable accuracy. This precision reveals not just that changes occurred, but how quickly they unfolded. One of the most important insights from ice sheet records is that climate does not always change gradually. While ice ages build slowly, warming events can be abrupt. In some periods, temperatures rose sharply over just a few decades or centuries. These rapid shifts, sometimes called abrupt climate events, are clearly visible in ice cores. They show sudden changes in isotope ratios, dust levels, and gas concentrations. These events demonstrate that the climate system can reorganize itself quickly once certain thresholds are crossed. Ice sheets respond to these shifts, but they also influence them. As ice grows or melts, it alters atmospheric circulation, ocean currents, and surface reflectivity. The ice is not just recording change. It is participating in it. Dust layers in ice cores offer another window into past climates. During glacial periods, dust concentrations in ice dramatically. This reflects stronger winds, drier landscapes, and exposed continental shelves. The composition of the dust reveals its origin, allowing scientists to trace wind patterns and infer atmospheric circulation. Dust from distant deserts can be found thousands of kilometers away, embedded in polar ice. Volcanic eruptions also leave their mark. Ash layers preserved in ice cores provide time markers that can be correlated across different regions. These layers help synchronize climate records from around the world. They also show how volcanic activity can influence climate temporarily by injecting particles into the atmosphere that reflect sunlight and cool the planet. Ice sheets even record changes in solar activity. Variations in certain isotopes, such as beryllium-10, are linked to changes in cosmic radiation reaching Earth, which in turn are influenced by solar output. These subtle signals add another layer of information to the ice archive, connecting Earth's climate history to broader processes in the solar system. The phrase "ice sheets remember everything" is not exaggeration. They remember temperature, atmospheric composition, wind patterns, volcanic activity, ocean chemistry, and even biological changes occurring far from the poles. Each layer is a snapshot of a moment in Earth's past, preserved with a fidelity unmatched by most other natural archives. But ice sheets also remember in a more physical sense. Their sheer mass leaves lasting impressions on the planet's surface. When ice sheets grow, they weigh down the crust beneath them, sometimes by hundreds of meters. This depression alters drainage patterns, tilts landscapes, and affects sea level locally and globally. When ice melts, the land slowly rebounds in a process called isodic adjustment. In some regions, this rebound is still ongoing thousands of years after the ice retreated. This delayed response is another form of memory. The Earth beneath former ice sheets continues to adjust long after the climate has moved on. Coastlines rise, lakes tilt, river paths shift. These changes are slow, but they persist, reminding the planet where ice once stood. Ice sheets also influence sea level in ways that carry memory forward. When ice grows, sea level falls. When it melts, sea level rises. These changes reshape coastlines and marine ecosystems. Coral reefs grow or drown. Estuaries form or vanish. Sediment deposition patterns change. Long after an ice age ends, its influence can still be seen in submerged landscapes and drowned river valleys. From a biological perspective, ice sheets have repeatedly reorganized life on Earth. During glacial periods, vast areas become uninhabitable. Species retreat into refuges. Populations fragment. Genetic diversity is reshaped. When ice retreats, organisms expand into newly available land, often following different paths than before. This repeated contraction and expansion has been a powerful engine of evolution. Humans are no exception. Our species emerged and spread during a time of intense glacial cycling. Migration routes, population bottlenecks, and cultural adaptations were shaped by advancing and retreating ice. The distribution of languages, genetic lineages, and early technologies all bear the imprint of ice age dynamics. Ice sheets may not remember humans individually, but they remember the conditions that shaped human history. Despite all this, ice sheets are not permanent. They grow and shrink. They advance and retreat. Their memories accumulate, but they can also be erased. When ice melts completely in a region, the archive disappears. This has happened many times in Earth's past. Earlier ice sheets formed and vanished long before modern ice cores existed. Their records are lost, leaving gaps in our understanding. What remains, however, is enough to reconstruct a detailed picture of the last several ice age cycles. This picture shows a planet governed by long-term rhythms punctuated by sudden shifts and stabilized by feedbacks that can both resist and amplify change. Ice sheets sit at the center of this system, both responding to and shaping the climate around them. They are not passive victims of cold. They are active components of Earth's climate machinery. Their growth alters albedo, atmospheric circulation, and ocean currents. Their melting releases fresh water that can disrupt ocean circulation and trigger abrupt climate changes. Their presence or absence sets the stage for everything else. In this sense, ice sheets do not just remember the past. They influence the future. The current state of polar ice carries forward the legacy of previous glacial cycles. The thickness, extent, and internal structure of today's ice sheets reflect conditions that prevailed tens or hundreds of thousands of years ago. That inherited structure affects how ice responds to present and future warming. Layers within ice sheets can deform under pressure, flow around obstacles, and fracture under stress. These physical behaviors depend on temperature, impure content, and crystal structure, all of which are shaped by past climates. The ice's memory is not just chemical. It is mechanical. As modern climate change accelerates ice loss in some regions, scientists are racing to extract and preserve ice cores before they melt away. Each lost section of ice is a lost chapter of the Earth's history. The urgency here is not just about sea level rise or ecosystem disruption, but about preserving knowledge. Once ice melts, its memory is gone forever. At the same time, new discoveries continue to emerge from existing cores. Advances in analytical techniques allow scientists to extract more information from smaller samples. Subtle signals once invisible are now detectable. The ice continues to speak, revealing details about Earth's past that were previously hidden. All of this reinforces a central truth about ice ages. They are not just cold intervals marked by frozen landscapes. They are complex states recorded in extraordinary detail by ice itself. To understand why ice ages begin, persist, and end, one must listen to what the ice remembers. When ice spreads across continents and cold tightens its grip on the planet, life does not pause or politely step aside. It adjusts. It shifts. It endures in ways that are often quiet, incremental, and invisible until viewed across long stretches of time. Ice ages are sometimes framed as periods of biological hardship. And in many ways, they are. Habitats shrink, food webs are disrupted, extinction rates rise. But there are also periods of intense creativity in the history of life. Times when adaptation becomes not just useful, but essential. To understand life under ice, it helps to let go of the idea that organisms respond to climate change as a single coordinated group. There is no universal strategy. Each species reacts according to its own limits, behaviors, and evolutionary history. Some migrate, some shrink their ranges, some alter their physiology, some disappear, and some surprisingly thrive. The most immediate impact of advancing ice is the loss of habitable land. As ice sheets expand, they cover forests, grasslands, wetlands, and entire ecosystems. Regions that once supported rich communities become uninhabitable, not gradually, but decisively. Thick ice does not offer compromise. It eliminates habitat entirely. For plants and animals living in the path of advancing glaciers, survival requires movement. Migration becomes the dominant strategy. Species shift their ranges toward the equator or toward lower elevations, following climates that resemble the ones they evolved in. Forests retreat southward. Grasslands expand into areas once too cold. Animals follow the plants they depend on. Over thousands of years, entire ecosystems slide across continents, leaving behind only traces of their former presence. This movement is not smooth or uniform. Geography complicates everything. Mountain ranges block paths. Oceans interrupt land corridors. Deserts expand in some regions as cold reduces precipitation. What results is fragmentation. Populations that were once connected become isolated in pockets of suitable habitat, often referred to as refuges. These refuges are among the most important biological features of ice ages. They are places where conditions remain just tolerable enough for species to persist, while the surrounding world becomes hostile. In Europe, southern peninsulas serve this role for many plants and animals. In North America, regions south of the major ice sheets acted as reservoirs of biodiversity. In these refuges, populations survive, but they do not remain unchanged. Isolation alters evolution. When populations are cut off from one another, gene flow is reduced. Local conditions exert stronger influence over time. This can lead to divergence as populations adapt to slightly different environments. Some differences remain subtle. Others become profound, eventually producing new species. Ice ages, by repeatedly fragmenting and reconnecting habitats, have acted as engines of diversification. Cold itself also selects for specific traits. Animals in glacial environments tend to grow larger bodies relative to their surface area, reducing heat loss. Fur becomes thicker. Fat layers increase. Limbs shorten. These patterns are so consistent that they were recognized long before the mechanisms behind them were fully understood. They reflect basic physical constraints imposed by temperature. Behavior changes as well. Many animals alter their activity patterns, becoming more efficient in their use of energy. Migration becomes seasonal rather than permanent. Hibernation and torpor evolve or become more pronounced. Even animals that do not hibernate may reduce activity during the harshest periods, conserving resources until conditions improve. Plants face a different set of challenges. They cannot migrate as individuals, but populations can shift through seed dispersal over generations. During ice ages, tree species often retreat hundreds or thousands of km from their previous ranges. This movement is slow, limited by seed dispersal distances and the availability of suitable soil. As a result, plant communities reorganize themselves repeatedly. Some plants adapt to cold by shortening their growing seasons. They flower quickly, reproduce efficiently, and enter dormancy early. Others adopt low-growing forms that reduce exposure to wind and cold. Mosses, lichens, and hardy grasses become more prominent in glacial landscapes, forming the foundation of tundra ecosystems that can persist near ice margins. Life beneath the ice itself also persists in ways that are easy to overlook. Glaciers are not sterile blocks of frozen water. They contain microbial communities that live within the ice in meltwater channels and at the base where ice meets rock. These microorganisms metabolize slowly, drawing energy from minerals and chemical gradients. Their existence challenges assumptions about the limits of life and suggests that ice-covered worlds elsewhere in the universe might not be as lifeless as they appear. Beneath ice sheets, subglacial lakes form where geothermal heat and pressure melt ice from below. These dark, isolated bodies of water can remain liquid for hundreds of thousands of years. Within them, microbial ecosystems exist, entirely cut off from sunlight. Their survival depends on chemical energy rather than photosynthesis, offering another example of how life adapts to extreme conditions. Marine life also responds to ice ages in complex ways. As sea levels fall, shallow marine habitats shrink. Coral reefs are exposed or destroyed. Coastal ecosystem migrates seaward. Some marine species suffer severe range contractions. Others benefit from increased nutrient delivery as dust and glacial runoff fertilize oceans. Colder ocean temperatures alter circulation patterns, changing the distribution of nutrients and oxygen. Some regions become more productive. Others become less hospitable. Plankton communities shift, affecting the entire marine food web. Fish, marine mammals, and seabirds adapt by altering migration routes, breeding timing, and feeding strategies. One of the most striking aspects of life during ice ages is resilience. Even as conditions become harsher, life does not collapse wholesale. Extinctions occur, but they are selective. Species that can adapt migrate or exploit new niches persist. Those that cannot are replaced. Over multiple glacial cycles, this process reshapes ecosystems again and again. Humans are part of this story. Our species emerged during a time of intense climatic instability. Early humans did not evolve in a stable, warm world. They evolved in one that oscillated between cold and warmth, forcing constant adjustment. Migration, technological innovation, and social cooperation were not luxuries. They were survival strategies. As ice advanced, human populations followed retreating ecosystems. They adapted their diets, hunting strategies, and shelter construction to colder conditions. Clothing became more sophisticated. Fire use intensified. Tools diversified. These changes were not responses to a single ice age, but to repeated cycles of environmental stress. Ice ages shaped human movement across the globe. Lower sea levels exposed land bridges, allowing migrations that would otherwise have been impossible. Entire continents became accessible. Populations that were once separated found new routes to expand, mix, or diverge. These movements left lasting imprints on genetic diversity and cultural variation. At the same time, ice ages imposed limits. Expanding ice sheets blocked movement in some directions, creating bottlenecks. Populations were confined to narrower corridors of habitable land. These constraints amplified the effects of isolation and drift, further shaping evolutionary outcomes. What's important to recognize is that life under ice is not defined solely by suffering. It is defined by constraint, and constraint often breeds innovation. New behaviors emerge. New relationships form. Ecosystems reorganize themselves around different rules. The cold does not simply suppress life. It redirects it. This redirection leaves traces long after the ice retreats. Modern species distribution still reflect glacial history. Genetic lineages point back to ancient refuges. Patterns of biodiversity often align with past ice margins. Even agricultural potential in some regions is influenced by soils deposited by retreating glaciers. Ice ages also influence extinction patterns in ways that are not always intuitive. While cold periods are often associated with extinctions, rapid warming events can be equally disruptive. Species adapted to cold conditions may struggle when ice retreats quickly. Habitats change faster than migration or adaptation can keep pace. The end of an ice age can be as challenging as its onset. This asymmetry is important. Life under ice adapts to stability within cold conditions. Sudden shifts, whether toward warmth or further cold, test those adaptations. The fossil record shows that some of the most significant biological turnovers occur during transitions, rather than during the coldest phases themselves. From a long-term perspective, ice ages act as filters. They do not simply reduce biodiversity, they reshape it. Traits that confer flexibility, tolerance, and mobility are favored. Species that depend on narrow environmental conditions are more vulnerable. Over repeated cycles, these pressures influence the direction of evolution. The legacy of ice ages is therefore embedded in the living world around us. The forests you might walk through today, the animals you recognize, even aspects of human biology and behavior, all carry echoes of past cold. They are the result of survival under constraint, adaptation under pressure, and endurance through change. For all the patience ice ages seem to display while they are building, they carry a surprising capacity for sudden change. From a distance, the rhythm of Earth's climate looks slow and deliberate, almost stately. Ice advances over tens of thousands of years. Seas fall cimeter by cime. Ecosystems rearrange themselves gradually. Yet buried within that long calm are moments of abrupt transition. Episodes when the planet shifts gears far faster than anyone living at the time could have anticipated. These sudden thaws are among the most unsettling and fascinating features of Earth's climate history, because they reveal how quickly a world shaped by cold can begin to unravel. To understand these rapid warmings, it helps to remember that ice ages are not uniform blocks of cold. They are dynamic systems held together by a delicate balance of forces. Ice sheets, oceans, atmosphere, and sunlight remain locked in a feedback-driven equilibrium. As long as that balance holds, the system resists change. But once a threshold is crossed, resistance can give way to acceleration. One of the most striking lessons from ice cores and ocean sediments is that climate change does not always scale with its cause. A gradual increase in sunlight does not necessarily lead to gradual warming. Instead, the system can absorb that change quietly for centuries or millennia, appearing stable on the surface until something finally tips. When that happens, warming can surge forward at a pace that feels almost explosive by geological standards. These rapid warming events are often called abrupt climate transitions. They are not rare anomalies. They appear repeatedly in records of the last ice age, especially during its later stages. Temperatures in some regions rose dramatically within decades, sometimes even within a single human lifetime. Snow lines retreated. Ice margins pulled back. Ecosystems shifted faster than migration alone could easily accommodate. One of the clearest records of these sudden thaws comes from polar ice. Deep within the ice sheets, layers show changes in isotope ratios that indicate rapid warming. These shifts are not subtle. They stand out like sudden spikes in an otherwise steady pattern. Dust concentrations drop. Greenhouse gas levels rise. Everything points to a climate system that changed state quickly, not gradually. What makes these events especially surprising is that they often occurred while the planet was still firmly within an ice age. The background conditions remained cold, ice sheets were extensive, sea levels were low, and yet within that cold framework, regional climates flipped rapidly from glacial to near interglacial conditions, only to sometimes slip back again just as quickly. A key player in many of these sudden thaws is the ocean, particularly the circulation patterns that move heat around the planet. During glacial periods, large amounts of fresh water are locked up in ice sheets. But ice sheets are not perfectly stable. They can melt at their edges, releasing pulses of fresh water into the ocean. This fresh water is lighter than salty seawater, and can disrupt the sinking of cold, dense water that drives deep ocean circulation. When this circulation weakens or reorganizes, heat transport changes dramatically. Regions that once received little warmth from the ocean can suddenly be flooded with it. Temperatures rise quickly, ice melts faster, more fresh water is released. In some cases, this leads to feedback loops that accelerate warming even further. These disruptions do not always lead to sustained warming. Sometimes the system overshoots and then collapses back into cold. The climate of the last ice age appears to have flickered between states, especially in the North Atlantic region. Cold phases persisted for centuries, followed by abrupt warmings, followed again by cooling. To anyone living through such a transition, the world would have felt profoundly unstable. The suddenness of these thaws is part of what makes them so important. They show that ice ages are not uniformly slow processes. While their beginnings and endings may span millennia, their internal dynamics can produce rapid shifts that rival or exceed changes seen in much shorter climate records. From a physical standpoint, these abrupt transitions highlight the role of thresholds. Climate systems often behave nonlinearly. Small changes accumulate without obvious effect until a tipping point is reached. Beyond that point, the system reorganizes itself rapidly. Ice ages are full of such tipping points hidden beneath their slow outward appearance. One of the most dramatic consequences of sudden thaws is their impact on sea level. While the overall rise in sea level at the end of an ice age takes thousands of years, much of that rise can occur in pulses. Geological evidence suggests that there were periods when sea level rose several meters within a few centuries, perhaps even faster. Coastal landscapes that had existed for thousands of years would have been inundated within a few generations. Rivers changed course. Estuaries formed where valleys once stood. Freshwater ecosystems were displaced by salt water. Marine habitats expanded rapidly into newly flooded areas. For organisms adapted to stable coastlines, these changes would have been deeply disruptive. On land, rapid warming transformed ecosystems just as quickly. Tundra gave way to shrubland to forest. Species that attracted slow climate shift suddenly found themselves outpaced. Some adapted, some migrated quickly. Others disappeared from regions they had occupied for thousands of years. These biological responses are recorded in pollen layers, plant macrofossils, and animal remains. They show abrupt turnovers in vegetation and fauna, not gradual blending. The landscape did not ease into warmth. In many places, it lurched. Human populations living during these times would have experienced dramatic environmental change within their own lifetimes. Hunting grounds shifted, migration routes altered, water availability changed, resources appeared and vanished unpredictably. These pressures likely influenced cultural innovation, social organization, and patterns of movement. Importantly, these sudden thaws were not global in the same way as full ice age transitions. They were often regional, especially concentrated in the North Atlantic and surrounding continents. This regionality underscores the complexity of the climate system. Global averages can mask dramatic local changes. A world that is still technically in an ice age can nonetheless experience near-modern warmth in certain areas for centuries at a time. The causes of these abrupt events are still an active area of research. While ocean circulation plays a central role, it interacts with atmospheric dynamics, ice sheet behavior, and greenhouse gas feedbacks. The system is not controlled by a single switch. It is a network of interdependent components, each capable of amplifying or dampening change. One revealing feature of these sudden thaws is how they often precede larger, more permanent transitions. They act like rehearsals. The climate system tests warmer configurations, sometimes retreats, and then eventually commits. By the time the final deglaciation begins, the system has already demonstrated its capacity for rapid change. This history challenges the comforting notion that Earth's climate always changes slowly enough for life to adjust. While long-term trends may be gradual, short-term shifts can be abrupt and disruptive. Ice ages are not just slow descents into cold, followed by gentle recoveries. They're punctuated by surprises. These surprises matter because they reveal vulnerabilities. They show where the system is sensitive, where feedbacks can run away, and where stability can break down. They also reveal resilience, demonstrating how ecosystems and life forms have repeatedly survived rapid change, even when conditions shifted faster than evolutionary adaptation alone could manage. From a broader perspective, sudden thaws remind us that ice ages are not monolithic blocks of time. They are textured, uneven, and full of internal drama. Beneath the slow accumulation of ice lies a restless system capable of sudden transformation. Cold worlds can change quickly. That ice does not always retreat politely, and that the most dramatic moments in Earth's climate story often arrive without warning, hidden within patterns that otherwise seem reassuringly slow. When people talk about ice ages, they often speak about them as if they belong to a distant, almost mythic past. Something ancient sealed away behind mammoths and cave paintings, disconnected from the modern world of cities, satellites, and glowing screens. But from a geological point of view, the most recent ice age is not ancient at all. It is remarkably close. So close, in fact, that many of its consequences are still unfolding beneath our feet, along our coastlines, and even within the shape of the land itself. Geology has a very different sense of time than human memory. What feels unimaginably old to us can register as barely finished business on a planetary scale. By that standard, the last major glacial period did not end long ago. It ended just over 11,000 years ago. That may sound like a long stretch of time when counted in generations, but for a planet that measures its history in millions and billions of years, it is almost immediate. A pause between breaths, a brief interlude following an extended cold. The last glacial period reached its peak around 20,000 years ago. At that time, ice sheets covered vast portions of North America, Northern Europe, and Asia. Sea levels were dramatically lower. Coastlines lay far beyond where they sit today. Entire land bridges existed where oceans now separate continents. The planet looked familiar in outline, but profoundly different in detail. Then gradually at first and later more decisively, the ice began to retreat. This retreat marks the transition into the warm interval we live in, now known as the Holocene. From a geological perspective, the Holocene is extraordinarily young. It represents a brief warm phase within a much longer ice age that began millions of years earlier. The ice did not vanish entirely. Antarctica remained frozen. Greenland held on. Glaciers persisted in mountain ranges around the world. Earth never left its ice age state. It simply shifted into one of its warmer modes. What makes this recent ice age especially important is not just how close it is to us in time, but how thoroughly it shaped the modern world. The landscapes humans inhabit today were carved, deposited, scoured, and rearranged by the ice and by its retreating waters. Many of the environments we think of as natural baselines are in fact products of post-glacial adjustment. Consider the shape of continents. During the height of the last glacial period, so much water was locked up in ice sheets that sea levels dropped by more than 100 meters. Continental shelves were exposed. Rivers cut deep valleys across what is now seabed. Those valleys still exist, submerged beneath modern oceans. Coastal plains stretched outward. Islands were connected to mainlands. Migration routes opened and closed. When the ice melted, sea levels rose again, flooding those valleys and plains. The shorelines we know today are not permanent edges. They are temporary outlines drawn by the current balance between ice and ocean. Many of the world's great estuaries, bays, and shallow seas exist because glacial ice melted and allowed the ocean to reclaim low-lying land. The land itself bears equally clear marks. Glaciers are powerful sculptors. As they advance, they grind rock into fine sediment. As they retreat, they leave behind ridges, hills, lakes, and soils unlike anything produced by rivers alone. Vast areas of North America and Europe are covered by glacial till, a mixture of clay, sand, gravel, and boulders deposited directly by ice. These deposits influence agriculture, hydrology, and ecosystems to this day. Fertile soils in some regions owe their existence to glacial sediments. Poorly drained landscapes reflect the uneven way ice retreated and melted. Thousands of lakes, especially in northern regions, occupy depressions carved or dammed by ice. The abundance of fresh water in certain parts of the world is a direct inheritance from the last ice age. Even mountain landscapes that seem timeless were reshaped recently. Valleys widened into U-shapes. Peaks were sharpened by cirques. Entire drainage systems were rerouted. These changes are not ancient relics from deep time. They are legacies of the most recent cold. The climate itself also remembers this recent ice age. The holding has been relatively stable compared to the glacial periods that preceded it, but it has not been static. Temperatures have fluctuated. Precipitation patterns have shifted. Ice has advanced and retreated within mountain regions. Sea levels have continued to rise slowly as remaining ice adjusted to the new warmth. What stands out about the Holocene is not perfect stability, but relative consistency. Compared to the wild swings of the last ice age, the Holocene offered a climate window narrow enough for long-term planning. Seasons became predictable. Ice margins stabilized far from the tropics. Sea levels rose to near modern positions and then slowed. This consistency created conditions under which agriculture could emerge and persist. Human civilization did not arise simply because the ice age ended. It arose because the climate entered a phase that stayed within certain bounds for long enough. Crops could be domesticated. Settlements could remain in place. Trade routes could develop. Surpluses could be stored. The holding did not guarantee civilization, but it made it possible. From a geological perspective, this coincidence is remarkable. For most of human evolutionary history, climate was highly variable. Glacial cycles repeatedly disrupted habitats. Resources shifted. Populations moved. Then, just as humans developed the cognitive and social tools needed for complex societies, the climate settled into a relatively stable warm interval. That stability should not be mistaken for permanence. Geological records show that previous interglacial periods were also warm and relatively stable, but none lasted forever. Each eventually gave way to renewed cooling as orbital cycles continued their slow progression. The Holocene, by this measure, is not unique. It is simply the most recent example. This is where the phrase "a very recent ice age" takes on its full meaning. We are not far removed from glacial conditions. We are living in their aftermath. Many systems are still adjusting. The planet has not fully equilibrated to the end of the last glacial period. Sea levels are still responding. Ice sheets are still changing shape. The crust beneath formerly glaciated regions is still rebounding. In parts of northern Europe and Canada, land is still rising as it slowly recovers from the immense weight of ice that pressed it downward. This rebound continues at measurable rates. Today, coastlines shift not only because sea level changes, but because the land itself is moving upward. Harbors must be adjusted. Infrastructure must account for these changes. The ice age is still physically present in the landscape's behavior. The oceans, too, carry memory of this recent past. Deep ocean circulation patterns reflect conditions established during glacial periods. Carbon stored during colder times continues to influence atmospheric composition. Nutrient distributions trace pathways shaped by ice-driven sea level changes. The ocean has not forgotten the cold, even as surface conditions warmed. From a biological standpoint, many species are still expanding from glacial refuges. The distributions of forests, animals, and even microorganisms often reflect post-glacial migration patterns. Genetic studies reveal bottlenecks and expansions tied to ice retreat. Some species have not yet recolonized all the habitats that would seem suitable today. Their absence is not due to current climate, but to historical constraints. Human societies also reflect this legacy. Early migration routes followed ice-free corridors. Coastal settlement patterns were shaped by rising seas. River systems formed by glacial melt influenced the locations of early civilizations. Even cultural myths and oral histories in some regions appear to preserve memories of changing coastlines and retreating ice. Seen this way, the last ice age is not a closed chapter. It is an ongoing influence. The world we inhabit is a post-glacial world, still settling into the shape defined by the end of widespread ice cover. This perspective matters because it reframes how we think about the present climate. Modern conditions are not the long-term norm. They are a moment within a larger oscillation. The warmth we experience today exists against a backdrop of recurring cold. That does not diminish its significance, but it does place it within a broader context. Geologically speaking, the Holocene is brief. Some interglacial periods in the past lasted longer, others were shorter. The timing of their endings depended on orbital cycles and internal feedbacks. Based on those cycles alone, Earth would eventually be expected to cool again, allowing ice to expand once more. What complicates this expectation is the unprecedented rate at which greenhouse gases have increased during the industrial era. This added warmth has likely extended the current interglacial beyond what orbital forcing alone would produce. How long that extension lasts remains uncertain. The system is operating under conditions that have no direct analog in the geological record. Still, the closeness of the last ice age serves as a reminder of how responsive Earth's climate can be. The difference between a glacial world and a world that supports widespread agriculture is only a few degrees in global average temperature. That difference is enough to move ice sheets hundreds of km, raise or lower seas by tens of meters, and rearrange ecosystems worldwide. From a human perspective, the last ice age feels like deep history. From Earth's perspective, it feels like yesterday. The planet has not settled into a permanent warm state. It is paused mid-cycle, carrying the memory of cold forward into a warmer moment. The ice age we often think of as ancient is, in geological terms, barely finished. Its fingerprints remain everywhere in the shape of land, the depth of oceans, the spread of life, and the stability that allowed modern civilization to arise. The cold has not vanished into the past. It has simply stepped back close enough that its influence can still be felt, quietly shaping the world we take for granted as the present. Humans did not step onto a calm, settled planet and then slowly shape it to their needs. They arrived during a time of restlessness, when the climate was already shifting, when ice advanced and retreated, when landscapes transformed faster than traditions could fully settle from a geological point of view. The timing is striking. Our species emerged, spread, and diversified not after the ice ages had finished their work, but right in the middle of them. Humans did not inherit a stable world. They learned to live inside a moving one. The earliest members of our species appeared roughly 300,000 years ago, during a period when Earth's climate was already locked into strong glacial cycles. Ice sheets expanded and contracted. Sea levels rose and fell. Habitats fragmented and reconnected. For any organism trying to survive and spread, this was not an easy environment. Yet humans did not merely endure these conditions. They expanded across continents under them. This fact alone tells us something important about human adaptability. Our bodies are not especially specialized for cold. We lack thick fur. We're not particularly fast. We're not exceptionally strong. What allowed humans to survive repeated cold phases was not physiology alone, but flexibility. Behavioral flexibility, social flexibility, and technological flexibility. As ice advanced in the northern hemisphere, environment shifted southward. Grasslands replaced forests in some regions. Deserts expanded in others. Coastlines moved outward as sea levels dropped. Rivers carved deeper valleys. For human groups living in these changing landscapes, survival required constant adjustment. Food sources changed. Migration routes shifted. Seasonal patterns became less predictable. Rather than remaining tied to a single habitat, humans followed resources. When conditions worsened in one region, populations moved. This movement was not random wandering. It followed ecological corridors shaped by ice. Ice sheets blocked some paths entirely, forcing detours. Other areas opened temporarily, creating narrow windows of opportunity. Lower sea levels played a crucial role here. During glacial periods, vast quantities of water were locked in ice sheets, exposing land bridges that do not exist today. These bridges connected continents, allowing humans to migrate into new regions. What are now islands were once extensions of mainlands. What are now seas were once plains crossed by rivers and animals. These migrations did not occur in a single wave. They unfolded gradually, punctuated by pauses, retreats, and expansions. As climates fluctuated, human populations fragmented into smaller groups, isolated by ice, mountains, or deserts. Over time, these groups diverged culturally and genetically. When conditions improved and barriers eased, some groups reconnected, exchanging ideas, tools, and genes. Cold periods placed particular pressure on survival strategies. Food scarcity became a recurring challenge. Plant resources dwindled in colder regions. Large animals migrated or declined. Humans responded by broadening their diets, developing new hunting techniques, and improving food storage. Cooperation became increasingly important. Sharing resources reduced individual risk. Knowledge of seasonal cycles became a matter of survival. Fire was central to this adaptation. Control of fire allowed humans to generate warmth, cook food, and extend activity into colder and darker periods. Fire transformed energy intake, making previously inedible foods accessible and improving nutritional efficiency. It also altered social structure, creating gathering points that supported communication, learning, and bonding. Clothing and shelter evolved alongside fire use. Simple coverings became more sophisticated garments. Shelters became better insulated, more permanent, and better adapted to local conditions. These innovations were not static inventions. They were refined repeatedly as groups encountered new environments and colder extremes. Ice ages also influenced human cognition in subtle ways. Living in a world where conditions changed unpredictably favored planning, memory, and social coordination. Knowledge had to be transmitted across generations. Skills had to be taught, not rediscovered anew each time. This encouraged the development of language, storytelling, and cultural traditions that preserved information beyond individual lifespans. The cold also shaped human movement patterns. Seasonal migration became common. Groups followed animals along predictable routes. Camps were established and abandoned in rhythm with climate and resource availability. Over time, these patterns became embedded in cultural practices and social organization. Importantly, humans did not simply retreat from cold environments. They entered them. Archaeological evidence shows humans living in high latitudes and harsh climates during glacial periods. These were not marginal populations clinging to survival at the edges. They were established communities with tools, traditions, and social networks suited to cold conditions. This expansion into cold regions required more than endurance. It required innovation. New hunting tools appeared. Projectiles allowed safer hunting of large animals. Bone and antler tools supplemented stone. Sewing needles enabled fitted clothing. Each of these developments reduced the cost of cold and increased the range of habitable environments. At the same time, ice ages imposed limits. Population sizes remained relatively small. Resource constraints prevented large, dense settlements. Human presence was widespread but thin. These limitations shaped social dynamics, favoring flexibility over permanence. When ice retreated during warmer phases, humans expanded again, filling newly available landscapes. Forests spread, wetlands formed, coastlines shifted inward. Resources diversified. Human populations grew. Then as cooling returned, contraction followed. This repeated pattern left a deep imprint on human history. Genetic studies reflect this cycle. Bottlenecks appear during cold phases. Expansions follow warming. Diversity increases as groups spread, then narrows as habitats shrink. Modern genetic variation carries signatures of these ancient movements, shaped by ice-driven geography. Culture, too, bears the mark of cold. Mythologies, rituals, and symbolic behaviors may have roots in environments where survival depended on shared meaning and cooperation. Art and ornamentation appear in archaeological records during glacial periods, suggesting that even under harsh conditions, humans invested in identity, expression, and social cohesion. It is tempting to think of ice ages as obstacles that delayed human progress. In reality, they shaped the form that progress took. Humans became a species defined not by dominance over a single environment, but by the ability to move between environments. The cold did not stop this process. It trained it. As the last glacial period began to W&E, humans were already widespread. They did not wait for the climate to stabilize before expanding. They adapted to instability itself. When warming accelerated, human populations were poised to take advantage of new conditions. The transition into the warmer interval we live in now did not suddenly transform humans into a different species. The skills that supported agriculture, settlement, and complex societies were built during the Ice Age world. Planning, cooperation, tool-making, and social learning all predate the Holocene. What changed was the environmental context in which those abilities operated. With ice retreating and climate stabilizing, strategies that had once emphasized mobility could shift toward permanence. Fields could be tended year after year. Structures could remain standing. Surpluses could be stored. None of this erased the Ice Age legacy. It built on it. Understanding that humans arrived just in time for the cold reframes our place in Earth's story. We are not creatures of stability that later learned to cope with change. We are creatures of change that briefly encountered stability. The adaptability we often celebrate is not a modern trait. It is ancient, forged under pressure. This perspective also tempers assumptions about what is normal. The environmental conditions that allowed cities, states, and global networks to emerge are not Earth's default. They're a temporary configuration within a long cycle. Human history unfolded during a pause, not an end point. It is enough to recognize that humanity's arrival was not poorly timed. It was precisely timed. Our species emerged when adaptation mattered most, when flexibility was rewarded, and when survival depended on understanding a world that refused to stay the same. There is a common way people talk about ice ages that quietly implies a clean ending, as if the planet enters a frozen phase, endures it, and then emerges into a new stable normal where the cold has been permanently resolved. The language itself encourages that idea. We speak about ice ages in the past tense. We talk about them as events that happened, not as conditions that persist. But when you look closely at Earth's climate history, and especially at how ice behaves over long spans of time, that neat conclusion never really appears. Ice ages do not end in the way stories usually do. They loosen, they retreat, they reorganize, but they do not disappear. From a scientific perspective, this is not a matter of interpretation. It is a matter of definition and structure. An ice age is not defined by how much of the planet is frozen at any given moment. It is defined by the presence of large permanent ice sheets on land. As long as those ice sheets exist, Earth remains in an ice age. By that standard, we are still living inside one. Antarctica alone contains enough ice to dominate the planet's climate system. Greenland adds to that influence. Mountain glaciers persist across multiple continents. The cold has not been eliminated. It has been confined. This distinction matters because it changes how we understand climate transitions. The end of a glacial period like the one that peaked around 20,000 years ago is not the end of an ice age. It is a shift within it. A movement from a colder mode to a warmer one, while the underlying structure remains intact. The same mechanisms that allowed ice to expand are still present. They have not been dismantled. They are simply operating under different boundary conditions. To see why ice ages never truly end, it helps to think of Earth's climate system less like a switch and more like a balance with deep grooves worn into it. Over millions of years, repeated glacial cycles have carved preferred states into the system. Cold states with extensive ice sheets are one of those preferences. Warm interglacial states are another. The system moves between them, but it does not erase the path it took to get there. One of the reasons ice ages persist is the sheer inertia of ice itself. Large ice sheets are not fragile. They are massive, slow-moving structures that respond gradually to changes in temperature and sunlight. Even when warming begins, ice does not instantly melt away. It thins. It retreats at the margins. It breaks and flows. But the core can remain for tens of thousands of years, especially when it sits on high ground or in regions isolated from warm air and water. Antarctica is the clearest example. It has remained ice-covered through multiple interglacial periods. Temperatures rose, sea levels climbed, forests spread in the northern hemisphere, yet Antarctica stayed frozen. Its ice sheet grew and shrank at the edges, but it never vanished. Its position over the South Pole, combined with the circumpolar ocean currents that isolate it, creates conditions where ice is remarkably stable. Greenland tells a similar, though slightly more vulnerable story. Its ice sheet has survived repeated warm intervals, thinning and retreating during the warmest phases, but persisting overall. Its elevation plays a key role. Ice sitting thousands of meters above sea level experiences colder temperatures than surrounding lowlands. This elevation feedback allows ice sheets to maintain themselves even when regional climates warm. Because these ice sheets persist, they continue to influence the climate system long after glacial periods end. They reflect sunlight. They shape atmospheric circulation. They affect ocean currents through freshwater input. As long as they exist, they exert a cooling influence on the planet. This means the climate never fully resets to a pre-ice age state. It remains constrained by the presence of ice. Another reason ice ages never truly end lies in the orbital mechanics that drive them. The slow variations in Earth's orbit, tilt, and wobble do not stop when a glacial period ends. They continue cycling endlessly. The conditions that favor ice growth weaken during interglacial periods, but they do not vanish. Eventually, those conditions strengthen again. This is why interglacial periods are temporary by nature. They occur when orbital configurations increase summer sunlight enough to reduce ice. But those configurations are transient. Over tens of thousands of years, they shift. Summer sunlight decreases again. The balance tips back towards snow persistence. The machinery that produced ice in the first place is always waiting in the background. Importantly, this does not mean every interglacial is identical. Some are warmer than others. Some last longer, some end more abruptly, but none permanently disable the system that produces ice. Each interglacial is a pause, not a conclusion. The atmosphere reinforces this persistence. During interglacial periods, greenhouse gas concentrations rise, strengthening warming. But these increases are limited by natural feedbacks. Oceans eventually absorb excess carbon dioxide. Vegetation patterns stabilize over long time scales. Atmospheric composition tends to drift back toward levels that allow cooling when orbital forcing align. In other words, the climate system has a built-in tendency to undo extremes. Warmth invites processes that dampen it. Cold invites processes that dampen it. But the damping is uneven. It slows transitions rather than preventing them entirely. The result is oscillation rather than convergence on a single stable state. Ice ages are also reinforced by geography. Continents are arranged in ways that favor ice formation at high latitudes. Large land masses sit near the poles, especially in the northern hemisphere. Land cools faster than ocean. Snow accumulates more easily. Ice sheets can grow. If continents were arranged differently, Earth's climate history might look very different. Because the continents move only over tens of millions of years, this geographical setup persists across many glacial cycles. The stage remains the same. The play repeats with variations. Ice ages are not accidents of a single configuration. They are the expected outcome of Earth's current layout. From a geological perspective, the current ice age itself is part of an even longer story. Earth has experienced multiple ice ages throughout its history, separated by long, warm intervals lasting tens or hundreds of millions of years. The present ice age, which began around 2.6 million years ago, is not the first, and it will not be the last. What distinguishes it is its rhythm driven by orbital cycles, interacting with continental positions and atmospheric composition. Seen at that scale, ice ages do end eventually, but not in the sense people often mean. They end when the underlying conditions that support them change fundamentally. Continents shift, mountain ranges erode, ocean gateways open or close. Atmospheric chemistry evolves over millions of years. These changes alter the climate system so deeply that glacial cycles lose their footing. We're nowhere near such a transformation now. The continents are essentially fixed on the time scales that matter for ice ages. The orbital cycles remain intact. The ice sheets persist. By all geological measures, the ice age we're in is ongoing. This understanding reframes how we think about the present warm period. The Holocene is not a permanent escape from ice. It is a mild phase within a long, cold era. Its relative stability is unusual, but not unprecedented. Past interglacials also experienced warm, stable intervals before cooling resumed. What makes the current situation unique is not that the ice age is ending, but that an additional warming influence has been layered onto it. Human activity has increased greenhouse gas concentrations far beyond what natural processes would produce at this point in the cycle. This added warmth has delayed the return of glacial conditions, and altered the trajectory of the system. Yet even this influence does not erase the Ice Age framework. It pushes against it. It stretches the warm phase. It reshapes feedbacks, but the long-term orbital packing remains. Unless human activity continues to dominate climate forcing for tens of thousands of years, the conditions that favor ice will eventually reassert themselves. This does not mean ice will suddenly surge back. It means the system retains its capacity for cold. That capacity never goes away as long as ice sheets, orbital cycles, and continental geometry remain in place. Another reason ice ages never truly end lies in the way the climate system stores memory. Ice sheets remember past climates through their structure. Oceans remember through heat and carbon storage. Soils remember through accumulated organic matter. Even the crust remembers through deformation and rebound. These memories influence how the system responds to new forcing. When warming occurs, it does so on top of these memories, not on a blank slate. The system's response is shaped by where ice remains, how oceans circulate, and how land has been sculpted by previous glaciations. This inherited structure makes complete erasure of Ice Age influence impossible. There is also a psychological dimension to the idea that ice ages end. Humans experience climate over short spans. A few generations of warmth can feel definitive. Landscapes without ice can feel permanent. But Earth's perspective is different. It measures change in layers, not lifetimes. From that perspective, the absence of ice in mid-latitudes is a brief condition, not a resolved state. This mismatch in time scales often leads to misunderstanding. When people hear that the last ice age ended, they imagine a finished process. In reality, they're hearing about a transition between modes within an ongoing system. The ice withdrew, but it did not relinquish control. Understanding the ice ages never truly end predicting imminent catastrophe. It means recognizing continuity. The forces that produced ice are still part of the system. They are quiet now, subdued by current conditions, but they are not gone. This perspective also helps explain why discussions of future climate can feel confusing. On one hand, there is long-term cooling expected from orbital cycles. On the other, there is short-term warming driven by greenhouse gases. Both are true, operating on different time scales. The Ice Age framework provides the backdrop against which these influences interact. Seen this way, Earth's climate is not marching toward a single destiny. It is oscillating within constraints, influenced by both ancient rhythms and recent disturbances. Ice ages do not end with a closing scene. They fade into warmer passages, only to gather strength again later. For now, it is enough to hold on to a simple, but often overlooked truth. Earth does not move from ice to warmth and then settle. It moves back and forth within a long-lived cold era, guided by cycles that outlast civilizations. The ice retreats, but it does not say goodbye. It stays close enough to return whenever the balance allows it to do so. Even when the planet feels settled, when ice sits quietly at the poles and seasons arrive more or less on schedule, the deeper timing mechanisms that govern Earth's climate never stop running. They do not pause out of courtesy for civilization, and they do not reset simply because a warm interval has lasted longer than expected. Far above the atmosphere, beyond clouds and storms, and even beyond the moon's familiar pull, the clocks that regulate long-term climate continue their slow, precise motion. They tick without sound, without drama, and without regard for what happens on the surface below. These clocks are not mechanical devices, of course. They are patterns of motion written into the geometry of Earth's relationship with the Sun and with the rest of the solar system. Their pace is measured not in seconds or years, but in tens of thousands of years. To a human observer, they feel almost static. To the climate system, They are persistent signals that never truly fade into the background. The most important thing to understand about these celestial clocks is that they do not care about averages. They care about alignment. They regulate when sunlight arrives, how intense it is at particular latitudes, and how that energy is distributed across seasons. The total amount of sunlight Earth receives over a year changes very little. But the timing and placement of that sunlight changes constantly, and those changes are enough to reshape the planet when given time. At this very moment, Earth's orbit is slowly evolving. Its shape is becoming slightly more circular over a cycle that spans roughly 100,000 years. This change is subtle, far too small to notice from one lifetime to the next. But it matters because it reduces the contrast between Earth's closest and farthest approach to the Sun. That in turn affects how strongly other orbital effects can influence climate. At the same time, Earth's axial tilt is slowly decreasing. The planet is becoming a little more upright relative to its orbit. This reduces the contrast between seasons, especially at high latitudes. Summers become slightly cooler. Winters become slightly milder. For ice, this matters far more than it sounds. Cooler summers reduce melting. And reduced melting, sustained over thousands of years, is one of the essential ingredients for glaciation. Meanwhile, Earth's axis continues to wobble. This wobble shifts the timing of seasons relative to Earth's position in its orbit. Over long periods, it determines whether summers in a given hemisphere occur when Earth is closer to the Sun or farther away. Right now, northern hemisphere summers occur when Earth is relatively distant from the Sun. This slightly weakens summer sunlight compared to what it would otherwise be. None of these factors taken alone are dramatic. They do not cause abrupt cooling or warming by themselves, but together they create a long-term trajectory. They gently favor conditions that allow snow to persist at high latitudes. They do this slowly, patiently, without ever announcing that anything significant is happening. This is why the phrase, "the clocks in the sky are still ticking," matters. It reminds us that the same orbital mechanisms that governed past ice ages are still operating today. They have not been overridden or dismantled. They have not expired. They continue to move Earth toward configurations that under natural conditions would eventually support renewed ice growth. From a geological perspective, the current warm interval is already well underway. Interglacial periods in the past often lasted between 10 and 20,000 years. We're now more than 11,000 years into the present one. That does not mean it is about to end tomorrow, but it does mean it is no longer in its early stages. Orbital calculations show that summer sunlight at high northern latitudes has been declining for several thousand years. This decline is gradual, but it is steady. Left to its own devices, the climate system would likely be responding to this trend by very slowly allowing snow to linger longer in certain regions. Over many millennia, that lingering snow would begin the long process of ice accumulation. This does not mean glaciers would suddenly surge southward or that ice sheets would rapidly reappear. It means the balance would slowly shift. The planet would begin leaning toward cold again, just as it has many times before. What complicates this picture is the presence of a powerful additional influence layered on top of these celestial clocks. Greenhouse gas concentrations in the atmosphere are far higher than they would be under natural conditions at this point in the orbital cycle. This added warmth counteracts the cooling influence of declining summer sunlight. As a result, the climate system is currently being pulled in two directions at once. One pull comes from the slow, predictable geometry of Earth's orbit, nudging conditions toward eventual cooling. The other comes from rapidly increased atmospheric insulation, pushing temperatures upward. These forces operate on vastly different time scales, which makes their interaction especially complex. The orbital clocks tick slowly, almost imperceptibly. The atmospheric changes driven by human activity have occurred within centuries. From Earth's perspective, that is an instant. The climate system has not had time to fully respond or adjust. It is still absorbing heat, redistributing energy, and rebalancing feedbacks. This mismatch in pace creates a kind of tension within the system. The long-term trajectory has not disappeared, but it has been bent. How far it bends, and for how long depends on how persistent the additional warming influence remains. If greenhouse gas concentrations were to stabilize and then slowly decline over many thousands of years, the orbital clocks would eventually regain dominance. Cooling would resume. Snow would begin to persist again in key regions. Ice sheets would slowly grow. The ice age cycle would continue, delayed but not canceled. If, on the other hand, elevated greenhouse gas concentrations were maintained for tens of thousands of years, the system could behave differently. Ice sheets might be prevented from regrowing entirely. The current ice age could eventually be brought to an end in a geological sense, not through a single dramatic event, but through sustained alteration of atmospheric conditions. That possibility is one of the reasons scientists describe the present moment as unusual. The climate system has never experienced this exact combination of orbital forcing and atmospheric composition before. There is no perfect historical analog. The clocks in the sky are still ticking, but their influence is being partially masked. Still, masking is not the same as stopping. Orbital cycles continue to set the boundaries within which climate operates. They define what is possible over long spans of time. Even if their immediate effects are overshadowed, they remain the underlying framework. This framework is why discussions about the next ice age are not speculative in the way science fiction is speculative. They're grounded in mechanics that are well understood and mathematically predictable. The timing is uncertain, especially given current conditions, but the existence of the cycle is not. Looking backward makes this clear. Past ice ages did not begin because something extraordinary happened. They began because ordinary predictable motions accumulated their effects over long periods. There was no moment when Earth crossed a dramatic line and suddenly froze. There were only gradual shifts that eventually became unavoidable. The same principle applies now. The absence of advancing ice does not mean the system is neutral. It means other forces are currently stronger. Should those forces weaken, the long-term clocks will still be there, ready to reassert their influence. There is something humbling in this realization. Human history, for all its intensity and speed, unfolds against a backdrop of motions that are almost unimaginably slow. Civilizations rise and fall while Earth's axis barely shifts. Entire eras of technology pass, while orbital eccentricity changes by fractions of a percent. And yet those fractions matter. Given enough time, they have reshaped the planet repeatedly. They have determined where forests grow, where deserts expand, where ice accumulates, and where seas rise or fall. Understanding that these clocks are still ticking does not mean expecting immediate change. It means recognizing that stability is conditional. It depends on alignment. It depends on balance. And balance in Earth's climate system is always temporary. The sky above is not just a backdrop of stars and sunlight. It is a moving framework, quietly counting out cycles far longer than human memory. Those cycles have shaped ice ages before. They are still shaping the climate now. And regardless of what happens in the near term, they will continue ticking long after the present moment has passed into the geological record. The question sounds simple when it's asked out loud, almost casual. So when is the next ice age really? It's the kind of question that suggests there might be a date, or at least a window. Something you could circle on a calendar far in the future and nod to with a sense of distant inevitability. But the moment you try to answer it honestly, the simplicity falls away. What remains is a layered problem shaped by time scales that do not align, forces that operate independently, and a planet whose climate history resists needling. From the perspective of Earth's long rhythms, the question itself is reasonable. Ice ages have come and gone with remarkable regularity over the last few million years. Glacial periods expand. Interglacials interrupt them. The pattern repeats. There is no reason in principle to think that this rhythm has suddenly stopped. The clocks in the sky are still ticking. Orbital cycles continue their slow progression. Ice sheets remain in place. All the machinery that produced past glacial advances is still intact. If Earth were left entirely to those natural rhythms without any additional influences layered on top, scientists could offer a fairly straightforward answer. Based on orbital calculations alone, conditions favorable for renewed glaciation would begin to emerge tens of thousands of years from now. Summer sunlight at high northern latitudes would continue to decline. Snow would have an easier time surviving melt seasons. Ice would begin very gradually to accumulate. In that purely natural scenario, the next major glacial advance would likely begin somewhere between 30 and 50,000 years from now. Not as a sudden freeze, but as the slow reappearance of persistent snow fields that eventually compress into ice. The full expansion of large continental ice sheets would take many thousands of years beyond that. No single generation would witness the beginning and the peak. The process would unfold at Earth's pace, not ours. But that answer only holds if one critical assumption remains true, that the climate system is governed solely by the same natural forcings that shaped past cycles. And that assumption no longer holds. The presence of elevated greenhouse gas concentrations fundamentally alters the timeline. Carbon dioxide levels in the atmosphere are far higher now than they have been at comparable points in previous interglacial periods. This added insulation changes how the planet responds to declining summer sunlight. It does not eliminate orbital forcing, but it counteracts it. To understand how this changes the answer, it helps to imagine the climate system as a balance rather than a countdown. On one side of the balance sits the slow cooling influence of orbital cycles. On the other side sits the warming influence of greenhouse gases. For most of the last few million years, those two forces operated within a relatively narrow range. Orbital cooling would tip the balance toward ice. Greenhouse warming would resist it, but not overwhelm it. Today, that balance has been shifted. The warming side is much heavier than it would be naturally. As a result, the system no longer responds to orbital cooling in the same way. Modeling studies suggest that with current greenhouse gas levels, and especially if they remain elevated for a long time, the onset of the next glacial period could be delayed by tens of thousands of years. Some estimates suggest delays of 50,000 years or more. Others propose that if atmospheric carbon dioxide remains above certain thresholds, the current ice age could be effectively suspended indefinitely. This does not mean ice would never return under any circumstances. It means the natural trigger points that once allowed ice to gain a foothold would be much harder to reach. Snow would melt more completely each summer. Ice sheets would struggle to grow beyond their current limits. The system would remain locked in a warm bias state. At this point, the question, when is the next ice age, becomes inseparable from another question. How long will elevated greenhouse gas concentrations persist? That is not a question orbital mechanics can answer. It depends on human choices, technologies, policies, and behaviors. It depends on whether carbon continues to accumulate in the atmosphere, stabilizes, or eventually declines. It depends on how oceans and ecosystems respond over long periods. It depends on processes that operate on time scales far shorter than glacial cycles, but whose effects extend far longer. If greenhouse gas concentrations were to peak, and then gradually decline over the coming centuries and millennia, the orbital clocks would eventually regain influence. Cooling would resume slowly at first. The timeline for the next ice age would lengthen but not vanish. The planet would return to its familiar oscillation, simply shifted forward in time. If, on the other hand, greenhouse gas concentrations remain high for many tens of thousands of years, the outcome could be different. Ice sheets might retreat further. Greenland could lose much of its ice. Antarctica's margins could change substantially. The very definition of the current ice age could be altered. In that case, asking when the next ice age begins may no longer make sense in the way it once did, because the current one may have been brought to an end through sustained warming. This possibility highlights something important. Ice ages are not guaranteed, outcomes written into the planet's future regardless of what happens. They are emergent properties of specific conditions. Change those conditions enough, and the outcome changes too. That said, it is crucial not to misinterpret this as evidence that ice ages are fragile or easily erased. The climate system has enormous inertia. Ice sheets respond slowly. Oceans absorb heat and carbon over long periods. Even large perturbations take time to propagate fully. The system does not flip instantly into a new regime. Even with elevated greenhouse gases, some aspects of the ice age framework remain. Antarctica is likely to retain ice for very long periods due to its geography and isolation. Orbital cycles will continue to influence regional climates. The potential for cold has not been eliminated. It has been postponed, complicated, and reshaped. Another layer of uncertainty comes from the fact that past ice ages were not perfectly regular. While orbital cycles provide packing, the exact timing and intensity of glacial advances varied. Internal feedbacks, ice sheet dynamics, and ocean circulation introduced variability. This means there was never a single precise schedule to begin with. The question of timing also depends on what one means by the next ice age. Does it mean the first signs of persistent snow accumulation, the growth of major ice sheets, the return of full glacial conditions comparable to the last maximum? Each of these occurs on different time scales. Early signs could appear long before dramatic changes become visible. Persistent snow fields might form in certain high-latitude or high-altitude regions, while the rest of the planet remains broadly familiar. Ice sheets could grow modestly for thousands of years before expanding significantly. The transition would be gradual, not cinematic. From a human perspective, this distinction matters. The next ice age, even under natural conditions, would not be something anyone alive today or in the near future would experience directly. It would not arrive as an event. It would arrive as a trend, unfolding too slowly to notice without instruments and long-term records. This slow pace is why ice ages often feel abstract despite their immense impact. They do not align with human lifespans or planning horizons. They operate on a time scale where continuity is measured in millennia. So when people ask when the next ice age will happen, what they are often really asking is whether the current climate state is permanent. And the answer to that is no. It is not permanent, but it is not ephemeral either. It exists within boundaries set by both ancient rhythms and recent changes. Under natural conditions, the next ice age would still be far in the future. With current warming influences, it is likely much farther still. How much farther depends on how the climate system evolves over the coming thousands of years, not decades. This perspective can feel unsatisfying because it refuses to offer a clear date or countdown. But it is also more honest. Earth's climate does not operate on schedules designed for human convenience. It responds to balances, thresholds, and feedbacks that do not align neatly with calendars. There's also a subtle but important point often missed in discussions of the next ice age. Preventing or delaying glaciation is not inherently good or bad in itself. Ice ages are not moral events. They are states the planet enters under certain conditions. Warm periods are not rewards. Cold periods are not punishments. They are different configurations of the same system. What matters from a human perspective is not whether ice ages occur, but how rapidly and unpredictably the climate changes. Slow transitions allow adaptation. Abrupt shifts create stress. Ice ages, for all their cold, are often characterized by slow change. Rapid warming or cooling is far more disruptive. Seen this way, the concern is not that the next ice age is coming too soon. It is that the system is being pushed in ways that could produce unfamiliar behavior, including abrupt transitions that do not resemble past patterns. The question of timing then is best reframed. Not when is the next ice age, but under what conditions does Earth return to a state where ice can once again expand naturally? And how do current conditions alter that return? The honest answer is that under current atmospheric conditions, the natural return of widespread glaciation is unlikely for many tens of thousands of years. The orbital clocks point toward cooling, but the atmospheric insulation is strong enough to counteract that signal for a long time. Whether that delay becomes a permanent diversion depends on factors that are still unfolding. The system has not yet reached equilibrium with current greenhouse gas levels. Oceans are still warming. Ice sheets are still responding. Feedbacks are still playing out. In other words, the timeline is still being written. What can be said with confidence is that ice ages are not surprises that arrive unannounced. They are the culmination of long detectable trends. If and when conditions begin to favor renewed ice growth, scientists will see it coming long before it becomes obvious to the naked eye. For now, the planet remains in a warm phase within a longer cold era. Its future shaped by both ancient celestial rhythms and very recent atmospheric changes. The next ice age is not imminent. It is not scheduled on a human time scale, but it is also not a relic of a finished past. The machinery that produced ice ages is still there. The clocks in the sky continue their slow count. Whether those clocks are allowed to complete another cycle depends on forces that are for the first time in Earth's history being significantly influenced by a single species. Living on Earth often feels like living on something solid, dependable, and settled. The ground beneath your feet does not usually suggest indecision. Mountains stand where they stood yesterday. Coastlines appear fixed. Seasons arrive in a familiar order. From the inside, the planet feels resolved, as though it made up its mind long ago and has been sticking to it ever since. But when you widen the view, when you step back far enough in time, a very different picture emerges. Earth is not indecisive in a human sense. But it is never finished deciding. It changes its mind slowly, methodically, and with a patience that can make those changes feel invisible until they are already well underway. One of the hardest things for humans to grasp is slowness on a planetary scale. We are adapted to notice change when it happens within our own lifetimes or within the stories we inherit from our parents and grandparents. When change stretches across thousands of years, it dissolves into the background. It becomes the stage rather than the action. Ice ages fall into this category. They are not events we remember. They are conditions that quietly frame human history, shaping it without ever demanding attention in a single dramatic moment. This is why it can be so difficult to reconcile two truths at once. The first is that Earth's climate is always changing. The second is that on human time scales, it often feels stable. Both are true because the planet's pace of decision is so slow that its movements blur into continuity. A few thousand years of warming or cooling can transform continents, yet pass without ever feeling like a turning point to the people living through it. Living on a planet that changes its mind, slowly means inhabiting a world where causes and effects are separated by long delays. A shift in sunlight distribution today may not fully express itself in ice or oceans for thousands of years. Carbon released into the atmosphere may linger long after the activity that produced it has faded into history. Ice that begins melting now may continue reshaping coastlines long after societies have adapted to the initial change. This delay creates a strange psychological effect. It encourages the belief that the present state of the world is somehow earned or permanent, that the climate we experience is what Earth prefers. But preference is a human concept. Earth responds. It does not choose. And its responses are guided by balances that drift gradually rather than snap decisively. Throughout this exploration, a recurring pattern has emerged. Ice ages do not arrive suddenly. They build through accumulation. Warm periods do not end abruptly. They erode through small imbalances sustained over time. The planet rarely announces its intentions. It simply follows them. For most of human history, this slow pace worked in our favor. Gradual climate change allowed populations to migrate, adapt, and innovate. Even dramatic transitions like the end of the last glacial period unfolded slowly enough to be absorbed across generations. Landscapes changed, but not overnight. Rivers shifted, but not between one season and the next. This gave life, including human life, room to respond. That historical context matters because it shapes how we interpret the present. The modern world is accustomed to rapid change. Technology evolves quickly. Cities transform within decades. Information moves instantly. Against that backdrop, it can be tempting to assume that the planet operates in a similar way, either remaining fixed until suddenly disrupted or changing quickly in response to immediate pressures. Neither assumption fits Earth very well. Instead, Earth accumulates signals. It integrates influences over long spans. When enough of those influences align, change follows, often in ways that seem inevitable only in hindsight. Ice ages exemplify this behavior. Each one was predictable in broad outline, long before it became visible in ice or stone. Yet none would have felt predictable from within. Living on a planet like this requires a different way of thinking about time. It requires accepting that stability is provisional, that the present is not a destination but a phase, that the conditions supporting forests, coastlines, and civilizations are maintained by balances that can shift without urgency but with persistence. This perspective does not diminish the value of the present moment. If anything, it deepens it. Recognizing that Earth's current state is temporary does not make it fragile in a trivial sense. It makes it precious in a geological one. Warm interglacial periods like the one we live in are not Earth's default mode. They are intervals carved out by a particular alignment of forces. They have beginnings, middles, and endings. Even if those endings lie far beyond human planning horizons, it also reframes the role humans play in Earth's story. For the first time, a species has become capable of influencing climate on time scales comparable to those slow planetary decisions. Human activity is now interacting with orbital cycles, ice dynamics, and atmospheric feedbacks in ways that would have been impossible for any previous life form. This does not make humans all-powerful, but it does make us relevant to processes that once operated entirely beyond biological influence. That relevance introduces responsibility, but not in a dramatic or moralized way. Responsibility in this context simply means awareness of time scales. It means understanding that actions taken over centuries can echo for millennia. That altering atmospheric composition does not just affect weather next year, but energy balance far into the future. That delaying or amplifying natural climate cycles reshapes the context in which future life will exist. At the same time, It is important to resist the urge to frame Earth as fragile or on the brink of collapse. Ice ages themselves are evidence of resilience. The planet has endured far colder and far warmer conditions than those of the present. Life has persisted through all of them. The question has never been whether Earth survives change. It always does. The question is how change redistributes opportunity, risk, and habitability. From that standpoint, living on a planet that changes its mind slowly means accepting that long-term outcomes are rarely reversible in simple ways. Once ice sheets grow to continental scale, they do not melt quickly. Once oceans warm and expand, they do not cool and contract overnight. Once coastlines flood, they do not return to previous positions without equally long reversals. This asymmetry is another defining feature of slow planetary change. Building takes time. Undoing often takes time too, but not always in the same direction or at the same pace. Ice builds slowly and can melt faster. Carbon accumulates quickly and is removed slowly. Sea levels rise steadily and fall only under very specific conditions. These asymmetries shape how transitions feel and how they are remembered. It's also worth noting that slow change does not mean gentle change. Ice ages reshaped continents. They displaced ecosystems. They reorganized oceans and atmospheres. Their slowness does not make them subtle in outcome. It only makes them subtle in experience. That distinction matters because it challenges the way humans often evaluate risk. We tend to worry about sudden disasters and underestimate slow transformations. A storm that destroys a city demands attention. A gradual shift in climate zones over centuries does not. Yet the latter can have far broader consequences over time. Ice ages remind us that the most consequential changes are often the quiet ones. Snow that lingers, ice that thickens, oceans that cool or warm by fractions of a degree, sunlight that arrives at a slightly different angle. None of these would draw notice on their own. Together, sustained over time, they transform the planet. Living with that knowledge does not require constant vigilance or anxiety. It requires perspective. It means understanding that Earth's history is not a straight line toward any particular outcome. It oscillates. It experiments. It revisits familiar states under new conditions. This understanding also tempers expectations about control. Humans can influence climate but not command it. We can nudge the system, amplify certain feedbacks, suppress others, and alter timelines. But the deep structure of Earth's behavior remains. Orbital cycles continue. Ice responds to gravity and temperature. Oceans redistribute heat according to physics, not policy. In that sense, humans have not replaced the planet's decision. We have joined it. Our actions now participate in the same long conversation between sunlight, ice, air, and water that has been unfolding for millions of years. There is something quietly grounding in this realization. It pulls attention away from the idea of a single decisive moment and toward the idea of continuity. Earth's future will not be determined by one choice or one generation. It will be shaped by the accumulation of many influences, some deliberate, some incidental, all interacting over long spans. Living on a planet that changes its mind slowly also means recognizing that patience is built into the system. The planet does not rush. It absorbs disturbances. It redistributes energy. It tests new configurations. This does not guarantee benign outcomes, but it does mean there is time to observe, learn, and adjust. Ice ages, for all their cold, demonstrate this patience. They did not arrive to punish life. They emerged because conditions aligned. They persisted because feedbacks reinforced them. They retreated when those alignments shifted. They are not enemies or errors. They are expressions of how Earth operates when left to its own rhythms. Seen from that perspective, the question is no longer whether Earth will change again. It will. The question is how prepared life, including human life, is to live within a system that never settles permanently. Adaptation has always been the answer. Not adaptation in a narrow biological sense alone, but cultural, technological, and psychological adaptation. Humans have already demonstrated this capacity repeatedly under Ice Age conditions. Migration, cooperation, innovation, and learning were responses to a world that refused to stay still. The modern challenge is different in detail, but similar in structure. It involves responding to slow-moving forces whose consequences extend far beyond immediate experience. It involves thinking in layers of time rather than moments. It involves accepting that the present is part of a larger arc rather than its conclusion. In the end, living on a planet that changes its mind slowly is less about predicting exact futures and more about understanding patterns. Patterns of accumulation, patterns of delay, patterns of feedback. Ice ages are one of the clearest expressions of those patterns, not because they are extreme, but because they are patient. They remind us that Earth does not hurry to become something else. It drifts there, carrying memory with it, responding to influences long after their origins have faded from view. And while that slowness can make change hard to notice, it also offers a kind of continuity, a sense that the planet's story is not rushed, even when it is profound. As this long exploration settles, the most useful takeaway may be a simple one. The world you inhabit is not finished. It is not fixed. It is in the middle of a process that began long before humans appeared and will continue long after current concerns have become history. Recognizing that does not diminish the present. It places it exactly where it belongs as one moment in a planet-wide conversation that unfolds at a pace far slower and far more enduring than any single lifetime.